Again, hello and good afternoon, everyone. Welcome to EIA's Energy Storage Workshop. My name is Patricia Hutchins. Today, we will have two panels, each with 3 speakers and a Q&A section. Again, please feel free to send along any questions during the panel presentations through the Webex Q&A feature, and we will do our best to include them in the Q&A section. We have a number of attendees at the workshop today. Thank you all for joining us, and we look forward to informative presentations and a lively Q&A discussion with our panelists. Now, I would like to introduce Tom Leckie, the Assistant Administrator for Energy Statistics here at EIA. In this role, Tom directs information programs covering energy consumption and efficiency, electricity, nuclear and renewable energy, oil, natural gas, and coal supply, and petroleum and biofuels production and marketing. Tom also manages the EIA data collection program, statistical methods, and quality control for weekly, monthly, quarterly, annual, and quadrennial statistical reports. Please, Tom, whenever you're ready.
Thanks a lot, Tricia. And thanks for the great pre-pandemic picture that you're showing. Look a little different, but maybe we all do. I want to welcome all of you here today. It's great for me to be here to introduce such an important and interesting topic. I want to start with just a couple of broad remarks about how EIA gets its data programs going. The enabling legislation that created EIA in 1978 required the administrator of EIA to run a comprehensive energy data program. And from the beginning, that's what we've always set out to do. In fact, some of the data series that we collect preceded the creation of EIA and DOE, as we were formed by several predecessor federal agencies associated with various energy groups. Since 1978, obviously, energy markets have grown, they've gotten more complex, and EIA has constantly been adding information to its portfolio. Today's discussion centers on one of our newest data series, battery storage and the associated characteristics of its operation. And one of the best parts of my job is giving the team the go-ahead to collect new data like this battery data. When we start collecting new data, oftentimes the early going can be tough. It's tough on respondents to assemble the data and report it to us and understand us through our forms, our collection forms, and what exactly it is that we're looking for. It's tough on EIA staff to interpret the information they're receiving for the first time, process it effectively, and it can be tough on data consumers who are looking at data series for the first time and trying to make sense of it, and trying to figure out what it means in their applications and in their markets. But the new data collection and bringing it to the public inevitably starts what I like to call a virtuous cycle. That is, we start in one place, and with every iteration of the data becomes more robust, and the effects of us collecting and disseminating the data also become more robust. The data gets better. The data that gets reported to us gets better. The data gets more widely consumed by people. It gets more broadly consumed in applications. And the sum result of all of this virtuous cycle is that markets become more robust, and the information that we're privileged to put into it becomes more powerful and more positive to markets. So with regard to the battery storage data, many of you are familiar with the fact that we put out our latest iteration of this annual data over the summer. I just want to call out a couple of the things that I thought were very interesting in our latest iteration. Energy storage represents the 4th largest technology capacity gain in 2020. And our data indicates that that projection is going to continue for the next several years. Wind, solar, natural gas combined cycle contributed more of the capacity, but batteries are projected to remain in front of what we would call bread and butter technologies like simple cycle natural gas capacity. So this is a robust, a young but robust portion of the dispatch. We use another metric, simply the count of generators. Batteries are the second most deployed technology in 2020, and we expect to deploy many, many more battery operations next several years. One of the earliest observations in the first few years of the data was that battery storage deployments seem to be heavily associated with RTO markets. But one of the latest observations is that batteries are being more widely deployed in non-RTO markets. In particular, we're seeing a lot of activity in Arizona, Nevada, and Florida. There's also been a significant shift in the use case profiles among battery operators. Frequency response is the most commonly cited application by operators of batteries, but increasingly we are seeing that arbitrage, not an ancillary service, not something that contributes to the stability of the system, has become a dominant service for batteries. Obviously, co-location with renewable resource is a major market driver, and we continue to see that in the data that is reported to us. In terms of existing battery deployments, 114 of the 255 batteries are co-located with renewable resources. So with that, I will leave you in the capable hands of the panelists. Really looking forward to the exchange of information today. And I can just tell you that, again, one of the most important things that we do in EIA is make sure the information we bring to the public is used and useful. And the way that we determine that it is used and useful is through public sessions like this, where, again, we are privileged to receive feedback and to understand better how the information is being deployed. So it's a pleasure to be here, and I really hope this is a great couple of hours. Tricia, back to you.
Thank you, Tom. I'm going to let Glenn take over from here to go on to panel one.
All right, thanks, Tricia. Thanks, Tom. My name is Glenn McGrath. I run a couple of the survey programs that provide much of the data around battery storage and where it stands in the industry, both in terms of capacity and operation. I'm going to overlap a lot of what Tom said, but this is important because a lot of these points are important to emphasize. At the risk of understatement, battery storage is growing very quickly. We started the year with just under 1,500 megawatts of it, and as of August, we have over 3,000 megawatts. No technology has seen that level of growth. Early years of solar are close, they're in the same ballpark. PV doubled in capacity from 2010 through 2013, but nothing nothing's doubled within 8 months within a year. So that battery storage is sort of blazing its own unique path, and it's challenging for us to track it. EIA is putting a lot of effort into keeping up with the growth. We've currently got 255 facilities with operational batteries, and we're tracking another 200 with planned batteries. We're also trying to put an important emphasis on getting the operational data out to the industry. Starting last year, for all storage systems, we started publishing gross generation, as well as continuing to publish net generation and consumption in our data sets. As a principal survey operations, we're forcing gross, net, and consumption to balance among the energy storage applications. Gross generation is, in our view, a critical indicator of battery storage activity, and that's why we've put a lot of emphasis on it recently. I make this point because a lot of activity can hide behind a negative net generation value. For example, we see batteries with negative 2,000, negative 4,000 megawatt hours over a course of the year. But the batteries with those values can have between 15,000 and 13,000 megawatt hours of gross generations. So you can see that gross generation is a critical thing to make sure we get out to industry. We've developed a metric, or not developed. We've published a metric that is similar to capacity factor. Capacity factor traditionally uses net generation. Well, we've developed a usage factor, published a usage factor, which switches out net generation for gross generation. And we publish that in our Electric Power Monthly, so you can see how batteries change over the course of the year. You'll see battery usage factors drop in the winter, and peak in the summer, and that should be fairly intuitive for us. It's important to note, I'm going to follow up on a few of the points that Tom made. It's important to note for the industry that EIA is very aware of the reporting burden that our data collection supply. We try very hard to minimize it. It's a Darwinian in effect. We found that when respondents understand why we're seeking the data and what we're doing with it and how we're trying to keep the burden low, they're more likely to provide better data to us. It's more timely, it's more accurate, and we think it serves the industry better. Collaboration leads to efficiency, accuracy, comprehensiveness, and meaning, and our staff operates with that awareness. And with that, I'm going to introduce Alex May. Alex is our leading storage expert in survey operations, and his contributions continue to remind me we made a great move bringing him on board back in 2016. Alex leads the operations of the 860 survey, which sets the frame and collects the design attributes for the existing batteries. Alex is one of the authors of the Energy Battery Storage Market Trends Report. And most importantly, as a Cleveland fan, Alex has demonstrated a humbling persistence that is a sign of a great team player, and that makes me very happy to introduce him. Alex?
Yeah, thank you, Glenn, for that introduction, and I appreciate the tie to Cleveland there. Hopefully the Browns can start turning things around. But yes, let me get my presentation up here. Before I jump into things, just want to let you know that I'll be walking you through some of the battery storage market trends as they relate to the EIA 860 electric generator report, which is what Glenn offered some background in. Also, just want to make a quick note. Whenever I mention large scale or utility scale energy storage, I'm referring to batteries over 1 megawatt in capacity, as that is the threshold that is required to report on the EIA 860. So to start things off with a few takeaways, as Glenn and Tom both mentioned, August 2021 was a fairly large year for energy storage. There's over 2,955 megawatts of battery capacity installed in the U.S. By that time, the operational battery storage capacity in the U.S. Doubled. Also, with the increase in the growth of capacity, we're also starting to see that California ISO and ERCOT, as well as other states, are taking up larger shares of the energy storage market. And at the same time, as Tom mentioned as well, batteries are also being used for a wider range and variety of use cases as that capacity grows. So much so that 61% of the expected battery storage capacity that come online between 2021 and 2024 will be paired with solar. And as we're seeing all this capacity growth, we're also starting to see a decrease in the costs of energy capacity. So far, between 2015 and 2019, costs dropped from $2,102 per kilowatt hour to $589 per kilowatt hour in 2019. Now to start to take a closer look at the data that we collect on the 860 as it relates to energy storage. Just going to step back a year to our most recent annual EIA 860 report. And at that time, before the most recent additions in August, 2020 was a record year in terms of annual battery installations with roughly 490 megawatts and 571 megawatt hours of batteries installed. That was roughly an increase of 47% and 32% respectively for both cumulative power and energy capacities. And before that time in 2020, the previous record was in 2018 with 222 megawatts and 507 megawatt hours of batteries installed. 2020 also saw an increase in annual additions from 2019, where it almost tripled in terms of power capacity and increased by 25% in terms of energy capacity. Looking at the time frame for this chart alone, we can also see that a third of the operational capacity came online in 2020 alone, before it doubled most recently in August. So this record, or this previous record year of capacity, was led by additions in both California ISO and ERCOT. So in 2020, California ISO made up roughly 57% of the power capacity additions, or 281 megawatts, and 48% of the energy capacity additions, or 270 megawatt hours. ERCOT made up roughly 22% of both power and energy capacity additions, with 109 megawatts and 126 megawatt hours. 2020 also saw an increase in relative growth in battery power capacity when compared to energy capacity. From 2018 to 2019, power capacity increased by 19%. However, from 2019 to 2020, power capacity increased by 47%. Growth in terms of energy capacity was a little bit more constant. Energy capacity growth between 2018 and 2019 increased by 34%, and then energy capacity from 2019 to 2020 increased by roughly 32%.
Hey, Alex, are we on the red slide for you? Alex,
oh yeah, we got the red slide. We're going well. Does everyone see the pie charts now? Because that's where I'm at.
Yeah.
Okay, great. So as I mentioned earlier, California ISO and ERCOT are making up larger shares of both energy and power capacities within the energy storage market. In terms of power capacity, California ISO, their share of power capacity increased from 20% in 2019 to roughly 31% in 2020. And then in ERCOT, their share of power capacity increased from 11% to 15%. In terms of energy capacity, California ISO's share of energy capacity increased from 36% to 38% in 2020. And then in ERCOT, the share of energy capacity increased from 6% in 2019 to 10% in 2020. Okay, you guys not seeing my... Are there issues with the presentation? I'm sorry if I'm getting some notifications here.
Alex, I've got your slides going, so you just let me know when we're going to move on to the next. We're on the pie chart slide right now.
Did it not share? Here, hang on. I could try and share my screen again. I'm sorry if that did not happen. All right, how about there? Apologies.
It looks good. Thanks, Alex.
All right, great. Sorry about that. But so we're seeing that increasing share in California ISO and ERCOT, but we're also seeing a decrease in the share in PJM, which in previous reports and presentations, there used to be a story of PJM and California ISO leading the way with energy storage. However, due to a lack of installations in PJM for 2020, their share of power capacity fell from 30% to 20% in 2020. Their share of energy capacity fell from 11% to 8% in 2020. Now I'd like to quickly go over our use case and applications data that we collect on the 860. Tom and Glenn both touched on this. On the 860, we ask respondents to select from a list of a variety of use cases concerning energy storage and what application they use their battery storage asset for. On average, respondents will cite usually 2.2 use cases per battery. So here I have data presented from 2019 with the ranks of energy storage ordered by their popularity or their most common selection. So for power capacity, frequency regulation is ranked at number 1. That's followed by ramping and spinning reserve coming in at 2, and then system peak shaving at 3. Excess wind and solar generation is coming in at 4, and then arbitrage is coming in at 5th. And in terms of energy capacity, we could see these ranks shift relative to those in the power capacity. So with coming in at number 1 is system peak shaving, coming in at number 2 is frequency regulation, and then coming in at number 3 is arbitrage, 4th is excess wind and solar generation, and then 5th is ramping and spinning reserve. Now, when we progress the year, we can see that the ranks begin to shift within the groupings of power capacity and energy capacity. Still at number 1 for power capacity is frequency regulation, and as well as number 2 coming in with ramping and spinning reserve, and then arbitrage rising up to 3rd, load following in 4th, and then excess wind and solar generation in 5th. And then in terms of energy capacity, arbitrage rises up to the lead use case. That's followed by frequency regulation coming in at 2nd, and then system peak shaving, ramping and spinning reserve, and then excess solar and wind generation. Now, to add a time element to this, to take a look at these top use cases over time, we're starting to note that better use cases are becoming more diverse as overall capacity grows. At the end of 2020, 885 megawatts of battery storage capacity, or 59% of the total utility scale battery capacity, cited frequency response as a use case. Arbitrage increased by 390 megawatts from 2019 to 2020. And then that was also the greatest capacity increase among all of the use cases. And then at the end of 2020, 586 megawatts of battery storage capacity, or 37% of the total utility scale storage capacity, was used for arbitrage. So this increase in various use cases is being led by additions in both California ISO and ERCOT, as well as in other states outside of the RTO region, such as Nevada and Arizona, and as well as an increase in the use of co-located and renewable paired energy storage assets. So much so that we expect to see very large increases for co-located and hybrid battery storage additions. Currently, only 1,529 megawatts of batteries are installed. 71% is standalone with 1.1 gigawatt, 13% is paired with solar with 192 megawatts, and 7% is paired with wind, 8% is paired with fossil fuels. Over 61% of battery storage to be added in the next couple of years from 2021 to 2024 will be co-located with solar. That's over 8.9 gigawatts. And then only 28% of that, or just right around 4 gigawatts, is expected to be standalone battery storage only. If planned projects become operational, 32% will be standalone with roughly 5.1 gigawatts. 56% will be paired with solar. That's just over 9 gigawatts. 3% will be paired with wind, and then 7% will be paired with fossil fuels. All in all, if all these projects come online, total battery capacity would be right around 16 gigawatts, over half of which will be paired with solar applications. Let's take a quick look at my Webex here to make sure everything's running properly. Now, breaking down these capacities by RTO region and by state, we can see that California ISO and ERCOT are making up a majority of paired storage applications in the RTOs, while Nevada and Arizona will make up a majority of the co-located storage applications outside of those regions, or outside of the market regions. 6.2 gigawatts of batteries are expected to come online between 2021 and 2024 in California ISO. 69% of which will be paired with solar. That's just over 4.3 gigawatts. And then 25% will be standalone, just over 1.6 gigawatts. And then 5% will be paired with fossil fuels. 1.8 gigawatts of batteries are to come online in ERCOT. That's 49% of which would be standalone. And then 27% will be paired with solar, or 502 megawatts. 15% will be paired with fossil fuels. And then 9% will be paired with wind. And then again, in Nevada and Arizona, we expect over 1 gigawatt of energy storage capacity to come online within each of those states. All of the batteries in Nevada will be paired with solar applications, while 93% of the energy storage in Arizona will be paired with a solar application, while the rest will be a standalone storage project. Now shifting over to a brief discussion of our cost data. Right here we have our costs broken down in terms of duration. And based off these charts, we can see that short duration batteries experience lower costs in terms of power capacity, while long duration batteries experience lower costs in terms of energy capacity. The average construction cost in terms of power capacity for short duration batteries is right around $872 per kilowatt. And then so it's slightly higher for long duration batteries, coming in right around $2,575 per kilowatt. The average construction cost in terms of energy capacity, you see these two groups flip. So short duration becomes more expensive at $2,329 per kilowatt hour, and then long duration becomes cheaper, right around $575 per kilowatt hour. Now, to look at energy storage as a whole, with the cost over time, we can see that the capacity weighted average cost in terms of energy capacity fell by 72% from $2,102 per kilowatt hour in 2015 to $589 per kilowatt hour in 2019. That's for an average annual decrease of 27%. In terms of power capacity, weighted average costs have remained relatively stable. The average cost range, or between an average cost range of $915 per kilowatt to $1,664 per kilowatt hour. This difference is likely a result of an increase in battery duration, as when we cut down and took a look at our battery cost sample, we saw that over time between 2015 and 2019, durations increased at a rate of 56%. So really just big takeaway here is that energy costs in terms of energy capacity are still declining, while power capacity costs remain relatively stable. So we're just seeing a more of a valuable metric here in terms of valuation on energy storage. But with that, I'll hand things back over to Tricia, and then we look forward to hearing what the rest of our panel has to share. Thank you.
Thanks, Alex. Tricia, if you don't mind, I can take it from there. I probably should have outlined a little bit the process. I was going to have each of the presenters provide the presentation. We have Jason Berwin up next and Cody Hill following Jason, and then we can entertain questions. We're right on schedule, so I don't want to preclude or discourage anybody asking questions as we go. Particularly, I think you might lose the train of thought by the time it comes around to the open question and answer period. So I'm going to kind of leave it up to the attendees. When asked questions, please go ahead and we're right on schedule. We have time to accommodate them. I think Alex did a good job pointing out that on the cost of batteries, when you use a per kilowatt basis, it can be a little tricky because they're adding they're adding attributes to the batteries that drive those costs up. But if you look at it on a dollars per kilowatt hour basis, costs are coming down, and I think we're going to see that in subsequent presentations. That seems to be a key trend. That batteries, the functional cost of batteries is the cost of the functional cost of the installed battery cost is coming down, and that's important. So unless anybody has any questions, I'll go right to the next presenter, which we're very fortunate to have, Jason Berlin, who is the interim CEO of the Energy Storage Association. Since I've been working in the storage area, Jason has been an ever present, and we're very fortunate to have him participate with us this afternoon. Jason is the interim CEO of the Energy Storage Association. He's been with the ESA since 2015, most recently as the Vice President of Policy. Previously, Jason was the Associate Director of the Energy Innovation at the Bipartisan Policy Center, where he directed research and advocacy on U.S. energy research and development and tax policy. He has also served as Staff Director of the American Energy Innovation Council, a group of CEOs led by Bill Gates to advocate for greater U.S. federal investments in clean energy technology development. Jason has also consulted utilities on demand response program design and evaluation for FSC Group, which was acquired by Nexent, and has reviewed renewable energy procurement processes and trends for the California Public Utilities Commission. Jason, we've got 20 minutes of a presentation. I'll turn it over to him and encourage questions come up. I'm happy to take them. But if we find better to hold on to questions at the end, that's fine too. Jason, you want to take it over?
Sure, Glenn. Happy to. Glad to be with you all today. Hello, everyone. Let me quickly just add that in addition to this, I am going to share my slides now. And I want to, there we go. Folks able to see my slides all right?
Yes, we can.
All right. So, Alex, I appreciate the work you did to present the quantitative information that's important here. So this makes it pretty easy for me in the sense that I will be able to recast some of this briefly from an industry side, and maybe that helps move us faster to a discussion and the other presenters. But overall, first, just for those of you who are not familiar with us, the U.S. Energy Storage Association is the national trade association representing all parts of the value chain in the energy storage industry. And we have primarily our membership focused on batteries and lithium-ion battery chemistries. However, we do represent a full range of not just electrochemistries, but also non-battery storage technologies, mechanical and physical storage media, thermal storage, and a little bit of power to gas storage as well. And we are all parts of the value chain from fracturer up through asset manager. I think that the perspective I'll provide is sort of a little bit more of an industry and market forward perspective. But I did want to at least first give my due credit to EIA's 860 series and show on a map where all these things are happening. That can help sort of illustrate where we are in time. So first things to notice from this map, which is as of August, and as was noted, EIA only tracks megawatt scale projects in front of the meter. The preponderance of these projects were early on clustered in wholesale electricity markets in PJM and ERCOT. California certainly, as you can tell, extremely full right now of both existing and planned projects, driven in part by the policy put in place the earlier part of the last decade to establish long-term deployment targets, but also more recently, very significant ramp up of build associated with meeting needs for local and system resource adequacy. And so that, as you can see here, there's an enormous amount in development as well in the California market. In Texas, the initial projects there were really smaller, fast frequency regulation projects. And we are seeing, again, sort of on a slight lag, but nonetheless quite significant build outs of projects, again, in the 100 megawatt scale, similar to what's been deployed recently in California. And that is driven much by the market fundamentals of the ERCOT market, rather than by, say, a explicit policy driver that has gotten the California market moving. In the Northeast there, certainly we have other states like New York, Massachusetts that have energy storage targets and programs as well. But I think that, you know, the changing nature of wholesale market rules, something we can get into certainly, is a part of what's driving development pipelines in those regions, the PJM region, New York ISO region as well. And then, you know, other things to look at on this map that you see, very significantly sized projects in some of the vertically integrated markets in Florida, in the American Southwest. And again, that's indicative of something that I think is going to be important to touch on, which is the nature of utility procurement moving from having ignored storage largely as of 4 or 5 years ago to now embracing it as a mainstream investment option for resource adequacy. So thank you, EIA folks, for making such fantastically simple data sets to use for mapping purposes. In terms of where we are at a global scale here, this is the storage decade. We are going from where energy storage is a fairly nominal part of power systems to a central part of power systems. And Bloomberg New Energy Finance just put out, I believe yesterday or 2 days ago, their global battery outlook report. And they note that they see globally a terawatt hour of stored energy capability being installed cumulatively to 2030. And if you look at that in the United States, they are forecasting about 100 gigawatts of cumulative battery installs, accounting for maybe somewhere around 350 gigawatt hours of stored energy capability, which you do your math, you can sense that a lot of this is expected to be projects that are capable of discharge at full nameplate capacity of 4 hours. But that itself will be changing, and we can get into that in a second. It's important to also note that the US is a leader and will continue, is expected to continue being a leader on this. And so I think that has significant implications, certainly, for the role that not only our markets and our policy play in informing the rest of the world how to bring energy storage into the systems, but also the importance of matters associated with supply chains and industrial policy. When you look ahead at the United States, this I'm going to be drawing from the information that our partners at Wood Mackenzie have brought together. We really expect a quite significant uptick. This chart in front of you is not an anomaly in the sense that someone turned the crank improperly on a model. The jump between 2019 to 2020 was quite significant, that first year in 2020 of a gigawatt of installed capacity, and is going to be dwarfed by what's expected to come online before the end of this year. A large part of that is the sort of longer term development plans now coming to fruition, both from IPPs who are bringing projects online in different wholesale markets, one of whom I believe Cody will be talking to you shortly about his experience, and also because of a number of, again, utility contracts that will be delivered this year. And we see that elevated level of deployment continuing into this decade. So really just from 2019 to 2021, kind of a level shift here, and now entering multi-gigawatt installations annually as a matter of course. When you look at it on a megawatt hour basis rather than megawatts, you can also see that these megawatt hours are increasing at a slightly faster rate, which I think is, again, instructive of the lengthening, quote unquote, duration of these storage facilities capabilities at full nameplate. And in both of these cases, you'll see that most of this growth is driven on the front of the meter. These very oftentimes much larger systems. This includes that distribution voltages too, and I don't want to overstate it, but I think that we are very likely to see increasingly significant build-outs at distribution voltages, but front of meter, depending on how regulatory processes update. And one of the reasons for that is that certainly folks in the storage industry are eager to make sure that they have oftentimes many options, and connection at distribution voltage provides an opportunity to do both local grid services as well as bulk system services. But nonetheless, this front of meter projection here rolls together both distribution and transmission voltages, and our expectation is transmission voltage storage will be the preponderance of these megawatts and megawatt hours for some time to come. Certainly, and one more note on this, those are the projections of deployments, but another signal here is what's making interconnection requests or otherwise seeking some sort of approval process for deployment. Various stages here, but WoodMac has followed this, and they find that we are seeing these requests for interconnection, many of which may be speculative, but nonetheless, I think are a signal of the expectations of the industry in terms of scales of deployment. So again, important to note, this is not the number of or the megawatts of projects that will come online. Many of these will not come online. These are simply queue requests or other approvals that have been cited. But I think it's instructive that the level of those requests has jumped quite significantly in just the last year, up to almost double where they were a year ago. So that gives you a sense of the future expectations of the market. And then, while I know EIA's research does not generally cover behind the meter, I think it's just important to at least give a brief look into the growth in these sectors as well. The relatively low percentage of deployment megawatts and megawatt hours from behind the meter is not a knock against behind the meter. It's really the much more the denominator here of much larger front of meter project deployments that makes them look proportionally smaller, perhaps up to 15-20% of deployments. But they are each on both in commercial industrial customers and residential market on growth paths. I think what's interesting is that the residential market growth path is projected to be much higher sooner than the commercial and industrial market. I do note I have not harmonized the scales on this slide, but it's important to see that the resi market is probably going to be the dominant one for some time to come. And that has implications for, again, regulatory considerations here. Certainly amongst the drivers, the critical biggest driver is cost declines. And thankfully, there's a lot more publicly available data sets on this than there have been. Thank you to so many folks at EIA and NREL and elsewhere. On the right-hand side here, this is pulled from the NREL ATB. And I think what's interesting to note here is just, again, a fairly, even if these are mid-level sort of estimates, that we are still seeing cost declines anticipated to continue for some time in energy storage facilities at scale, and that will have implications in terms of the durations of assets, quote unquote duration, that can be deployed economically on power systems, particularly as we see the capacity needs of systems potentially change over time with the supply mix and with the installation of energy storage of shorter durations. On the left-hand side here, something I just want to flag, this is actually very recently out from a working paper that I find really important to point out is that the cost declines in batteries have moved faster than expert projections, almost universally. And that's an important thing to bear in mind here, is that a large part of the modeling and expectations of futures on the power system have looked at storage too conservatively from the cost standpoint. And I think when you look at those red lines, which are expert projections, they continue to miss the steepness of these declines. That does not mean that we will continue to see uninterrupted cost declines forever, and certainly we will expect to see short-term anomalies potentially arising from, for example, global demand that outstrips ready supply in the near term as more and more manufacturing capacity comes online. But fundamentally, I think it's important from a modeling and future forward standpoint to recognize that we should expect expectations of cost to generally have been conservative and biased towards expecting greater declines and improved performance beyond sort of a conservative view here. In terms of the high-level drivers of deployment, these cost declines, as I noted, many of which are also driven not just by technology improvements, but learning by doing. Having folks install assets allows them to work out particularly the non-hardware costs, efficiencies. The RD&D in emerging technologies, that's not necessarily a near-term driver of deployment. However, as you start to look towards the back half of this coming decade, I think that those investments become significant in terms of helping to push emerging storage technologies down their cost curves more rapidly and making their economic deployment be able to happen sooner than without such investments. And certainly the recent emphasis on demonstrations in the IIJA may have a good role to play in that. From a market standpoint, no surprise here, increasing renewables deployments, increasing DER deployments are going to be drivers insofar as storage is able to either co-locate with those assets and utilize points of interconnection and siting efficiently and optimize those assets directly, or whether it's because, and I'm sure again other speakers will get into this, the nature of market pricing and market operations and grid operations will come to rely more and more on energy storage to effectively deal with the volatility of supply. From increasing DER deployments, this is something where storage becomes perhaps also part of more of a local grid infrastructure. As I've noted, one of the key drivers of a lot of deployments recently has been long-term contracts for resource adequacy. And that is itself a big change here, is that more and more grid operators that have capacity markets, utilities that are responsible for resource adequacy, see energy storage as fully capable of being a part of the system reliability, something that was not so common even just a couple of years ago. And so that is creating long-term contracting capabilities that will allow for these projects to be deployed more effectively at scale, given the capital intensity of large storage projects. The electrification of transportation, I think, is significant, both from an integration standpoint, in terms of bringing buffering the demands of electrified transport on the power system using storage to storage. Charging is going to likely be a part of DC fast charging infrastructure at scale, but also just, again, a recognition that like renewables deployment, like DER deployments, greater complexity of the systems, resourcing, supply mix, and demands and operations is going to create greater and greater value for having the flexibility that battery storage provides. And I might add, a non-trivial supply push part of this is the greater availability and, I would say, enthusiasm of private capital providers to invest in energy storage project deployment. Lowering the effective cost of capital for folks is very important. Having the ability to have large capital providers in place is something that gives developers the ability to create more positions, longer lead times, the kinds of things that from a business practices standpoint help you become a more effective deployer of assets. From the policy side, certainly decarbonization policies, at least indirectly, will continue to put an emphasis on using storage as a resource to complement, for example, non-dispatchable, zero carbon energy. But I also want to make sure that it's clear here that RTO and ISO market design reforms have been very critical for getting storage online. First, frequency regulation, a decade ago, and now specifically reforms to capacity accreditation of these resources, which we've seen in New York ISO and PJM, and a number of other practices and rules updates are helping to regularize energy storage as an asset in markets. And certainly I look at California ISO, as was noted, is deploying energy storage into wholesale markets, wholesale energy markets, as opposed to ancillary services markets, fastest. And we are just beginning to learn how that is affecting market operations and what additional market rules reforms may be necessary. State regulatory and planning updates. I made mention of state deployment targets, certainly as being a key driver. We have now about, I believe it's something like 12.5 gigawatts of energy storage deployment targets cumulatively across the United States, obviously by varying timeframes, but also other regulatory updates that are important, interconnection reforms that actually allow energy storage to be studied appropriately for what it is. Rate design, as has been discussed, particularly again, this front of meter distribution, voltage resources, planning updates, as I've noted, particularly in vertically integrated markets where utilities have integrated resource planning. That has been one of the areas of greatest regulatory development, has been a mixture of PUCs requiring consideration of storage in IRPs and a secular trend by utilities, not necessarily prompted by policy, but who are nonetheless now improving their modeling to be able to look ahead at future system needs and their supply mix to effectively model value energy storage in their planning and then choose it as a procurement basis. Last, federal incentives. Certainly right now, energy storage is able to avail the investment tax credit that solar power takes advantage of when integrated into solar facilities, one of the main drivers behind the hybridization of those assets together. Certainly, we could see, depending on legislation pending before Congress now, should a investment tax credit be made available for energy storage as a standalone asset, and particularly with some of the details in that legislation, that would accelerate the deployment of energy storage quite significantly. Friends at Wood Mackenzie, I think, estimate a 25% jump in installed capacity in the near term from such legislation being passed. And that will have interesting implications as well because of the nature of giving standalone storage this capability means that it will not be restricted in some respects to simply being a solar paired asset, and its operations then can be much more sort of fully optimized for whatever application it is being used for, which can be, again, an accelerant in how it's deployed. Anyway, I have done enough blathering, and so I will stop there for comments or questions, and I'm also happy to hand it to the next presenter if we want to do discussion right at the end of all the presentations.
Jason, that's a good point. I was thinking about there were some questions come in. They're good ones. I might give Cody the chance to give his presentation, and then we'll hit you up. Maybe the questions will be complimentary, and so we can handle them all at the end there. Thanks very much. That's very informative. I think we're going to get some good discussion out of the material you presented, and really appreciate you participating, Jason. On to Cody. Cody Hill is the next presenter, and he serves as Senior Vice President for Battery Systems at Rev Renewables. Prior to joining Rev Renewables, Mr. Hill has spent 7 years at LS Power, which is Rev's parent company, and focused on energy storage, including developing the Gateway facility, the world's largest lithium-based battery storage project, which is 250 megawatts when it was energized July last year. Previously, Mr. Hill was an engineer at Extreme Power. Mr. Hill holds a BS in electrical and computer engineering for the University of Missouri, Kansas City, and an MS in electrical and computer engineering with a focus on energy systems from the University of Texas at Austin. And we have done some work with the University of Texas, so that certainly jumps out at us. And we really welcome warmly Cody Hill too. And I'll turn the con over to you.
All right, thanks, Glenn. Can you hear me?
Yes.
Great. All right, and it's fun to follow Jason too. Jason and I have been in the industry for about an equal amount of time, but just on very different corners of it. So it's always interesting to hear his insights. And thanks to everybody from EIA for putting this on today and for the honor of the invitation. I really appreciate the chance to talk to you. I've used your work product many times over the years. So happy to give back a little bit with some time today. All right, so I'll keep it a little bit brief. I want to make sure we have lots of time for questions and to make this a discussion and kind of go in the direction you folks want to. But let's just jump into it. So Tricia, if you can please go to the next slide. All right. Just realized there's not very good contrast on this, but it's a map of the United States. This is where Rev Renewables has our operating projects and our offices. If you don't know Rev, we are a new company. We just launched earlier this summer in July. We have a pure focus on renewable energy, clean energy, and a very heavy, relative to most other independent power producers, energy storage focus. So we were spun out of LS Power. LS Power, not a household name, but we've been a owner-operator, developer, also a private equity group that buys and sells power plants and develops transmission, does all sorts of things in the power business for a long time. We did take kind of a core group from LS that has been in the clean energy side of things for quite a long time. It's a lot of experienced professionals. And we set up Rev, seeded it with all of our clean energy assets and our pure play focused on developing renewables, developing more energy storage. And there's just a tidal wave of capital available for investment in this. And you all know there's a huge, just a huge market opportunity over the next decade or so to deploy more clean energy as part of kind of an overall energy transition theme that is really worldwide. The one thing I'll just highlight on this map before we move on, there's kind of a smattering of solar projects all over the place. You'll see the battery storage projects are in green. Those projects are all what my group has developed and currently operates. So, by early next year, we'll have 615 megawatts operating across 4 sites, all in the California Independent System Operator market. And on the East Coast, we also own and operate a bunch of pump storage hydro, which really it does the same thing. So, I mean, the battery storage is kind of the modern technology, the most cost-effective new build. It's a lot easier to permit than something that has to, potentially flood a valley or get enormous water rights. But pumped hydro that's in the ground, it is a very important part of grid operations today, has been for decades. And as battery storage grows, I would suggest to you that you'll see kind of a convergence in how the two tend to operate. Let's advance the slide, please. All right, so just to kind of orient everybody, this is I'm going to use to anchor like the history part. So pumped hydro has been around for a very long time. Doing energy storage, it pumps energy, it pumps water up the hill to store energy and releases it back down through a dam later. This is a facility that we own in Pennsylvania, the Seneca Pumped Hydro. plant, which consists of upper and lower reservoir, and then the pumped kind of flying saucer looking upper tank that you can see up above. So very large scale facility. This was built in an era in the 1960s and 70s when there was still a lot of nuclear energy being built. And kind of the interesting thing is, because nuclear is not particularly flexible, doesn't ramp up and down, but load does ramp up and down. A lot of pumped hydro was built to help integrate all the nukes that were operating in the region. Also, a lot of the very large coal facilities in the region that are increasingly shutting down for economic reasons, they also were not particularly good at ramping and had very long start times. And so pumped hydro has always been there to provide more flexibility to grid operators and to match supply and demand on a long, slow scale, multiple hours over the course of a day. So since then, there has not been many new dams built in a very long time. It probably won't be, would be our view. So this is not probably a growth market, but it is something that's going to be part of things for a very long time. You can advance to the next slide. So today what we are building is battery energy storage. The shot below is an interior photo from the Vista Energy Storage Facility. It's a 40 megawatt battery that my team built a few years ago. Kind of looks like a data center. It's just racks of lithium-ion batteries. These are Samsung batteries. It's the same cell chemistry that goes into BMW electric vehicles and many other types of EVs around the world. And it's put into these racks that you can see kind of floor to ceiling. Each of these is about 8 feet tall. And the individual lithium-ion batteries are loaded. They're connected in series and parallel. And then what you can't see is that it goes outside to a set of inverters that convert the DC energy to AC and move the energy back and forth onto the power grid. I've been in this space since 2010. I started working on the first 1 megawatt battery in Hawaii, back when 1 megawatt was one of the largest projects being built in the world that year. We're in a very different space here 11 years later, but fundamentally this technology has not changed very much. There are lots of other battery chemistries that all work. I've also built molten sodium batteries and lead acid batteries over the years, but really 5-6 years ago, the lithium-ion industry ran away with the market and just had such an incredible cost decline and continued investment in technology, mostly driven by consumer electronics first and then the automotive sector second, that there really is no close second choice for what you're going to build if you're going to build a large energy storage facility today. There are lots of other technologies that work, and I think there's lots of other interesting things that are happening that deserve support at the pilot project level and deployment support to try and help them get to a higher level of maturity. But today, everything that's getting built is lithium ion to the tune of 95-99% of capacity being deployed. Just kind of rounding out the history part of things too. Early on, everybody was building very short duration batteries for very specific, very high margin applications. So originally that was integrating renewables in Hawaii, where power was unbelievably expensive. All the power came from diesel brought in on a boat, just most expensive power in the country. So it did make sense, even at high early technology costs, to build batteries for Hawaii back then. After that, you had PJM and ERCOT that had some interesting rule changes in the kind of early middle part of the decade that allowed batteries to provide frequency support with potentially a very small battery. You only needed like a 30-minute duration battery. And so you could build something at a reasonable capital cost and hopefully if the market didn't change, you'd be able to earn very good returns, 20% IRR type returns on something on the order of a $20 million investment was on a lot of slide decks back around 2012, 2013. We'll come back to that. It mostly didn't work out that way. Although you did see in Jason's map that a lot of those projects did actually get built. So that was where a lot of the investment happened in the middle part of the decade. Next slide, please. So today we are building projects, like I said, mostly in California. My group is. We're there. I know Jason said that one of the biggest reasons was the early policy push and the mandate for energy storage. I would actually argue that's maybe not even a top 5 contributor to the reasons that we're building things at the current scale that we are in California. We are building plants here because of huge economic fundamentals that are true here that are not yet true anywhere else in the United States. And frankly, I don't expect Eastern deployment of energy storage to look anything like it does in California until some of those other things come into place. The top 2 for me are, the huge amount of solar on the grid. Solar just naturally creates a need for intraday, support on the power grid, and batteries provide that better than anything. And additionally, California's goals to go to 100% clean energy, and specifically to shut down a lot of the oldest gas plants in the fleet, the ones that use once-through cooling that are located on the coasts first, but you do see a general interest in shutting down all the gas capacity in California. I don't know when or if that will ever happen, but the fact that it is so unthinkable to build something new with a smokestack in California means that this is the type of dispatchable capacity resource that you can build for the power grid today, and that's why we're doing it at scale. This facility that you can see here is the Gateway Energy Storage Facility. It is a 250 megawatt lithium-ion battery. When we initially energized it last summer, it was the largest project in the world. It has since lost that crown and then regained it due to some maintenance issues at the world's largest facility. We have expanded it since then, so we've now got 700 megawatt hours of operational batteries that are installed inside of these warehouse-style buildings. And what you're looking at, for those who have not seen these facilities, you've got the substation in the front. That's where the AC power comes in off the transmission grid, gets converted to medium voltage, 34.5 kV in this case, and that gets distributed underground to all these little boxes that you can see alongside of this long 70,000 square foot building. These little gray boxes are the transformers that convert the 34.5 kV to low voltage for the inverters. The white boxes, each one of these is about a 3 megawatt inverter. It converts the AC to DC, and then the cables go inside and they go to battery racks that look a lot like what you saw on the previous slide. Pretty much all of these battery storage facilities have that same architecture. It's 2 or 3 megawatt inverter stations is the most common. You can also see smaller ones sometimes. It's really the same technology that's used on inverters from the PV space, and so we've benefited from the scale of that much larger industry in being able to procure kind of higher volume and then lower cost, more mature hardware than we could back in the early days when I was doing this a decade ago. Let's go to the next slide. So this is another picture. This is the Diablo Energy Storage Facility. It is currently being commissioned in the northern part of the state. This is a 200 megawatt, 800 megawatt hour battery facility. Just at a glance, you can tell it's a totally different architecture. It is not in a big warehouse style building. It actually covers a lot more land than the other one. It's kind of hard to tell the scale, but this is about a 13-acre facility covered in hardware, whereas the other one was about a 4-acre facility covered in hardware with actually fewer megawatts here and a pretty similar number of megawatt hours between the two. So going to this containerized modular design has some benefits. It has some drawbacks, but just showing you, this is kind of the other flavor that you'll see out in the world where people are building storage projects. Next slide, please. All right, so what do we actually do with these things once we've built them? As Jason kind of teed up, there is a very large need for resource adequacy in California. RA, for those who are not California focused, is California's capacity construct. It is very complicated, I would say overly complicated in terms of its actual rules and regulations and how it is administered. But all of the load serving entities have to buy RA. Some of them have to buy it on a long-term basis, and the CPUC tends to direct procurement of new resources and uses the RA construct as kind of the way to get new capacity built in the state. So once they realized that they were short on capacity in the early 2020s through the IRP process, first the IOUs and now increasingly also the CCAs and the other load serving entities in California have all gone out and begun signing these resource adequacy contracts that lead us to build these resources. RA just creates must-offer obligations. It forces you to have the resource on and available to the California Independent System Operator, but it does not necessarily dictate how you are going to actually dispatch the resource. That is CAISO's job. You guys will hear from Gabe Murtaugh in a little bit. CAISO has complete control of how our resources are dispatched. There's nobody that has their finger on the controls of the plant. CAISO is the one telling us what to do, minute by minute, second by second, and it's based on the economic bids that we submit. CAISO has kind of the same mix of markets that really all the wholesale competitive markets have. All the ISOs have the same thing, maybe by different names, maybe by slightly different rules, but there's always kind of the same core items. There's always a day-ahead energy market where the vast majority of things get scheduled for the day. So 95% of CAISO's energy gets scheduled in the day-ahead market. They try their best to match hour by hour what they expect the load to be to a set of generation resources that are going to be online. And both our charge and discharge capability can get scheduled into the day-ahead energy market. Then during actual daytime operations, there's a real-time energy market. They try to close in the gaps if either the forecasts were not perfect, or if some resources do not show up, or if the weather is different and there's more load. Whatever it is, real-time energy is what takes that hourly granularity, turns it into minute by minute, 5-minute, and 15-minute granularity in the case of CAISO. So that's the real-time energy market. And then there's the ancillary services. So spinning reserve, frequency regulation. These are other things the batteries can also do. Probably too detailed to get into it a lot, except to say that frequency regulation is, of course, what a lot of batteries originally got built to do a few years ago in PJM. And I'll come back to that here in a couple of slides. So can we go to the next slide? So for the millennials and Gen Zers in the crowd who prefer memes, my in-house analyst made this and I liked it. So the thing to really understand about these markets is that going from left to right, you're going from much more duration necessary. You need hours of energy on the left. You need seconds or minutes of energy on the right. Batteries can be built and can access these things and potentially can earn very large margins on the short duration applications, and they're very large margins because it costs so much less. The cost of a battery facility is really mostly proportional to the dollars per kilowatt hour you're building. So smaller battery, more profitable if you can get paid the same dollars per megawatt is kind of the high level version on energy margins. The unfortunate thing for batteries, and especially for people in startups who are hoping to make lots of money doing value stacking and lots of frequency regulation and ancillary services, those markets are tiny. So CAISO is a huge market, 50 gigawatts of generation on a hot summer day. The total frequency regulation market, most hours, is like 300 or 400 megawatts. It's tiny. And so now that you already have thousands of megawatts of storage, that market's crushed. There is no opportunity there. It can be done with kind of leftover capacity, and you've already seen the prices decline massively. You will not see a lot of batteries doing a lot of frequency regulation that are new builds in California. Similarly, you will not see a lot of batteries doing frequency regulation anywhere else as soon as you get a few hundred megawatts of batteries into the market. So just expect that is not an ongoing source of investment in the space. Moving to the left on the hours side and talking about resource adequacy, that is robust. That is a tens of gigawatts opportunity. It is a much lower margin opportunity, but you will see thousands and thousands of megawatts in many markets built to operate in the day ahead and provide capacity and or resource adequacy depending on the market. Next slide, please. So you can kind of see that here. This I took straight off the CAISO webpage, 1 year apart. My projects were almost the only ones operating in early 2020, which is kind of interesting. There were very, very few batteries in the state of California, just a couple hundred megawatts of them last summer, 2020. And you can see that this is all the batteries in the state, and it totally adds up to a few tens of megawatts providing frequency regulation, kind of the telltale sign of frequency regulation. It's just this squiggly lines back and forth around zero output. You discharge a little if the frequency is too low. You charge a little if the frequency is too high. and you just wait for the signal from CAISO. Fast forward 1 year later, there are now over 2,000 megawatts that have been installed. And because the frequency regulation market has been crushed by all of this new entry, most of those megawatts, not because they want to do the lower margin activity, but because it's the only activity available to them, are charging in the middle of the day and discharging in the evening, which is great. That's that's how you integrate solar, and that's really the thing that people want to see batteries doing in the state of California, and it provides reliability because the state has the hardest time serving load in the evening hours after the sun goes down. So let's go to the next slide. And just to kind of wrap up here, I think this is really what the story is for the fundamentals of energy prices, right? As we move to more solar on the grid, there becomes a excess of energy available in the middle of the day to serve load. Power prices go very, very low. But that does not really do anything to serve load in the evening. In fact, it makes it a little bit harder to serve load in the evening because you don't have as many traditional gas power plants up and running to serve load. So you have to start them up, and ramp them right back down, which is a fairly expensive way to operate a gas plant. It causes more wear and tear in addition to not being particularly efficient. And so you have kind of a perverse thing happening where a lot of combined cycles are now being asked to, start, ramp, and shut back down as though they were simple cycle peakers, and that's not how they were designed, which probably over the long term will have some interesting kind of second order effects in the power market. As we go forward, you just expect this dynamic to increase and increase. California wants to get 30 gigawatts of solar, whereas it currently gets about 12. So you would expect that yellow, some people see a duck when they squint at it, shape that's on this thing, to grow and grow and eventually serve more than all load during the daylight hours of every day. So there will be tons of storage needing to shift that energy into the evening. And you can almost see that just by tracing out these lines. So I will stop there. There's lots of stuff that I think is interesting to talk about, but I've hit the main thing. So let's see where the questions go, and we can pick it up in the Q&A.
Great. Thanks, Cody. That was really informative. I'd had a sneak peek of the presentations. I knew it was going to be good, and lived up to it. We did get a lot of questions, and they're fairly evenly split between Jason and Cody. So I tell you, well, let me just go in order for lack of any better idea. The questions for Jason came in a little early, so I'll start with Jason. What factors do you see that could impede the kind of growth that Energy Storage Association is seeing? In other words, are there any issues with manufacturing, supply of critical materials, or other ramp-up factors that could come into play in an industry seeing such high growth rates over such an extended period of time?
Sure. I think that the concerns over the supply chain, in the short run, there is, an incredible amount of competition for battery supply globally. And, I think, though, many folks in the industry see that as perhaps a short-term anomaly, mostly affecting CODs, although I'm sure Cody can give a better insight from a developer standpoint. But how
short is short term, Jason?
Well, 2 years, 3 years. It depends in part, because what I was going to also say is that what we also see happening, of course, is increasing investment in expanding manufacturing capacity, and without making judgment on specific technology choices, I think the other piece of this to bear in mind here is, unlike the vehicle space, in which I think technology choices are fairly limited and narrow, in the grid storage space, you do have a number of different options. And again, in the short run, that may not relieve pressure from, say, a supply chain that's incredibly focused on lithium-based batteries. However, I would expect, again, over the medium term, for the latter part of this decade in particular, that the nature of those other alternatives also means that pressure on that supply chain is not going to be quite as critical for the future prospects of energy storage deployment as it might be for vehicles, which have really only, at this point, 1-2 choices of electrochemistries.
Okay. Another question for you, Jason. What areas of the U.S. do you see being more storage dominant than others? Will Texas and California always have no storage, or do you think 10 to 20 years from now, new areas, new leading areas will emerge? And what factors would lead one to deploy more storage in one area than another? In other words, are there other regions of the U.S. that are expected to add much more storage going forward?
Well, I mean, I think as Cody noted, the fundamentals that you see emerging in California with a very high renewables penetration, which I think all observers expect to be replicated in the ERCOT market as well, are going to be significant fundamental drivers. And we are going to see deployment, I think, at scale in other places. The question in my mind becomes the timeline for that. And also, well, I think that policy has certainly some role to play here. It also becomes a question of, perfect example, certain asset managers are going to make retirement decisions, some of which may be influenced by policy and some of which may not be influenced by policy. But for example, the recent decisions to retire fossil capacity across Pacific Cor's footprint means that approximately, I think it's 600 megawatts of battery storage are being deployed in combination with renewables to replace that retiring capacity across sort of the band from Oregon to Idaho, or I think Wyoming is included in that. And so what will be potentially important to watch then from my vantage point, Cody, I'd be interested to hear your thoughts, is the market fundamentals piece, the nature of policy drivers, and so, for example, what's driving it in places like Connecticut or Massachusetts or New York, and then finally, where you're seeing retirements happen on the near term, which have a very interesting geography across the Northwest, Southwest, center of the country, and Southeast.
Okay. Got a couple coming to Cody. This one's going to sound pretty similar to the one that Jason just fielded, or the first one Jason fielded. If factors, for Cody, if factors such as the big growth in EVs start to stress the supply of lithium-ion batteries, are there technologies of comparable cost ready to fill the gap? As you noted, it was mass production of in the EV sector that helped drop the cost for lithium, but perhaps too much EV growth could stress the supply chain. So I guess it's kind of a similar question, maybe your take on it.
Sure. Yeah, and I tried to kind of get at this a little bit. I mean, there are definitely other technologies that work. There's no question you could build something else that it is a battery connected to the power grid. But on comparable cost, and particularly comparable cost currently being built at scale by bankable suppliers that I can take to investment banks and get project finance, no, there's nothing else anywhere remotely close right now. I hope that there will be. There's lots of interesting things and good companies that are working on technologies that hopefully can climb that mountain to kind of achieve product market fit, but it's tough. And it's not a thing that happens overnight. So, you don't go from having a 5 megawatt pilot project to being able to do, a 200 megawatt power plant with all sorts of, reliability requirements placed on it by the grid operator in a matter of a year or even several years. I mean, it's going to take a decade for a lot of these folks to get to the scale where they're doing things that are power plant scale, like our projects are. But there's going to be lots of small, interesting projects in between them, and small means 5 and 10 megawatt. I mean, we're talking about tens of millions of dollars on some of these projects. They're not small by a lot of scales. It's just things on the power grid are big. Just to kind of add on to that, to the other part of it in the supply chain, it's not just the automotive supply chain that is the issue here either. The bad news for the whole industry is that projects are going to cost more next year, and probably in 2023 and probably in 2024 than they cost to build last year. And that's metals are up, both battery metals, lithium, cobalt, all of these things, but also steel. I mean, everything is more expensive right now, and nobody is currently willing to, assume that things return to the declining cost curves that we have all gotten so used to in the past few years. Shipping now costs about 5 or 6 times as much as it used to per unit of shipping container that you need to bring over. That's just gone through the roof in the past 6-9 months. It's hard to say when that normalizes. I think in the long term, certainly these things do get worked out, and probably some domestic manufacturing comes online. But right now, we are in a place where projects are going to cost more in the near term than they did before. But even still, I just see that slowing deployment. I don't see that being something that we switch over and start building gigawatts of anything else, because there are no factories producing gigawatts of anything else that are operating today.
Okay, all right, good answer. How about one more for you? Are any of the new energy storage assets being built without full capacity under contract? In other words, are any facilities not fully subscribed being built, or do you have to have your full output under contract to proceed?
Yeah, great question, and this has evolved over time. So in the early days, the PJM and ERCOT projects of 5-10 years ago, those were almost completely merchant projects. That was skilled developers and wind farm operators in a lot of cases that were able to, pull $20 or $30 million out of their balance sheet and do a pilot project in the name of expecting good returns, but also to get up the learning curve and other things. So there, lots of good investment happened there that was pure merchant, no contract backing it up, but finite size type of market opportunity, and that saturated very quickly, and not much else happened. Really until very, very recently, when people started getting back into Texas on the basis of kind of rosy expectations of high prices, $9,000 peak prices when things get constrained in Texas. And so you certainly can build some types of projects without any sort of a contract. It's much more common to see partially contracted at the very least. Maybe you've got an anchor contract for resource adequacy or something else that you can kind of take to the investment banks to get some of your capital. And then you try to earn a little bit more in the market, and so maybe it doesn't cover your entire economics with the contract. That's very, very common. But it is unusual at the power plant scale of hundreds of megawatts, and certainly the longer duration stuff almost always requires some amount of contracts. ERCOT's special though. It's a place where people build projects because they can and not necessarily because they should, is how I often describe it. Anybody who shows up with money in their pocket can get a project built in ERCOT within a year. And so there are lots of groups that are just putting dots on the map right now and building a 100-megawatt project because they have money to spend. Investors have said, go become a leader in energy storage. And you see a lot of those, and those are risk-on type of investments, which that's ERCOT. So it's kind of its own special place.
Indeed. What I guess kind of goes to another question, and this could be either for Jason or Cody. These were general, and I'm not really probably leave it a toss-up. When planning for resource adequacy, some RTOs, including ERCOT, assume that battery storage resources will provide ancillary services rather than sustained capacity to help serve peak loads. When do you think storage systems will become capable of providing the sustained capacity, and is there a threshold in terms of population and scale of operation that must be achieved to do that? I'm not sure if that's clear. Does that question sound clear, or should I try to restate that?
I mean, if I understood it, my answer would be that that's what happened 6 months ago in California, right? It's always been technically possible to do sustained capacity. People just didn't because they got paid more to provide frequency response. And that was totally how, every day we would, go into CAISO and say, here's the price to dispatch the unit for energy, here's the price to dispatch it for capacity. And they would every day pick it up for frequency regulation. And same resource, same bids. They just came in a year later and said, oh, now things have changed. The supply-demand stack has changed. We now want you to provide these multi-hour type of discharge and charge services. And that is, I think, what the questioner is getting at. So that's already happening. It's always been technically possible, and it's just now starting to happen because that's what the ISO sees as the least cost way to serve load overall.
Yeah,
To the operators. Yeah. Okay, I'm sorry, Jason.
I don't think grid operators in either vertical or wholesale markets are looking at storage as simply an ancillary services source at this point. That would be an outdated view of what storage is doing.
Along those lines, there's another one is the addition of significantly more wind capacity help a positive or negative outlook for battery storage? I guess grid operators are increasing the dispatchability of their wind fleet. So does that help or hinder energy storage? You know, the way the grid operators treating wind, I guess.
I mean, and Cody, I appreciate your perspective on this, but it depends because it depends on the portfolio, right? So ceteris paribus, more wind is going to be useful for deploying energy storage because of its non-dispatchability. However, it depends on the grid in which that wind is being provided, what the rest of the supply mix looks like. That determines in part what the value is of providing energy storage. So, you know, I think a wind-heavy grid that, you know, for example, lacks solar and has a ton of gas, just, you know, that'll have different fundamentals than a wind-heavy grid with a solar heavy or increasing solar deployment and less gas, right? And so, you know, to the extent that we want to talk about how important wind deployment is, you know, the general rule of thumb is more non-dispatchable renewables means more of a market opportunity for storage, but you really do have to look at the supply mix. You know, more wind in the Pacific Northwest, for example, gets balanced by hydro. So we're not really looking at a storage opportunity as much there. Cody, what do you think?
Yeah, no, that's exactly right, Jason. The wind, yeah, in a vacuum, sure, more wind, generally good for storage, although not a very strong relationship. You know, maybe it's a little bit better to have, you know, 10 gigawatts of wind in your local area than none. But you can integrate wind with gas. You can do it with hydro, and so in places that have no issue with running lots and lots of gas, probably it doesn't on its own create a big opportunity for battery storage. Certainly doesn't hurt. It's not like solar, where solar just creates a daily charge and discharge signal. You know, wind can go high for a week and then can go low for a week, and that's just one cycle for a battery, right? Whereas solar, every day there's going to be something to do, driven by a large amount of solar on your grid. If you're looking at battery storage, or pumped hydro, I mean, really any kind of storage has that dynamic. So the offshore wind on the East Coast, it's really hard to say how much storage that's actually going to prompt to get built. It's not a very direct relationship.
I guess a related question is the fleet of aging simple cycle turbines is going to require upgrades, investments, and I think you addressed this in your presentation. Do you see generators turning toward battery storage as replacements to those aging gas turbines?
Yes, and I mean, this is one of those, again, like you can't say this across the board because it's going to depend on the duty cycle of these assets, right? And also, the greater supply mix is other part of the generation fleet picking up some of the slack of capacity retirement. And so I think that, NREL and a number of other observers have quantified the capability of, for example, standalone battery storage of varying maximum quote-unquote duration to provide peaking capacity in the United States in various parts of the US. And I think those are a helpful guide for understanding a market sizing potential, but really on an individual unit basis, you're gonna have to know what the capacity factor of those assets is, and again, what else is on that system. We have seen one-for-one type of replacements, but I think that what's more likely is you're gonna see portfolio style replacements rather than one-for-ones. The other thing I'll also note here is that this is a question that I think is actually quite interesting, is the target the CT or is the target the CCGT? Because depending on that supply mix, the more renewables you have put into a grid, unless they are curtailing significantly, the run cycle of those CCGTs is going to start looking much more peaky and short than, might be typically sustained by a mid-merit generator. Again, Cody, I think you have some direct experience in looking at this, but that has significant impact on the economics of those plants. And so I think that this is not a simple like swap kind of discussion. You really do have to take account of what the capacity that's being retired is and what it's going to be replaced with, and what the supply mix looks like going forward on those grids. But the short answer is, yeah, of course, a lot of storage is going to replace retiring capacity.
Yeah. I mean, just to add to that, certainly if you've got retiring capacity, you've probably got a transmission line and a substation that you can interconnect to. That's a really valuable asset that you're not going to want to just bulldoze. You're going to want to repower it with something, and so either you're going to want to repower it with a new modern gas turbine or with battery storage. Typically, these sites are not big enough to put solar. Solar takes hundreds or thousands of acres for a very large scale project, whereas gas and batteries are single digit or tens of acres. So you won't see a lot of renewables replacing those retiring gas assets. Jason's point is exactly right. I'm more bearish on combined cycle economics for the long term than I am for kind of traditional peaker turbines. I do expect in a lot of markets where we're going to get to near 100% clean energy, maybe high 90s, whatever it is, you're going to still have the gas around for a really long time to provide reliability services. People are just going to need gas for those long multi-day periods. Maybe it all only has 5% capacity factors, and you're mostly paying for it on a capacity basis. But the economics are much better to be a simple cycle turbine in that type of a case where you're only running a few days a year than to have a great big combined cycle plant with $20 million of annual fixed O&M. Plus, it was not designed to start ramp and then ramp back down. That's something that is stressing all of the thermal connections and the steam paths that were designed to be built as baseload type of generation. So I'm very bearish in the places that are going to go heavy renewables on combined cycles. And actually, I think the combustion turbines will be around with us for a long time. Like GE LM 6000s. I mean, that is a very flexible, very fast starting type of unit. There are other manufacturers that have things like these. Those are going to be with us as part of the power mix for a long time, just hopefully running not very much if the goal is lowest emissions.
And if I may just say, I think that's precisely the point here. Flexibility is the value, right? So the less flexibility your units have, the more at risk you're going to be putting those assets, which is also part of the reason why we're starting at least a little bit to see batteries being hooked up to gas turbines directly because of this need for flexibility.
Yeah, it's interesting. Cody, by the way, your meme deployment was highly recognized by many commenters.
My analyst Brian is awesome with those. So follow him on Twitter.
I had a few more questions, but I did want to be respectful of everyone's time. We were going to run this till 2:30, and we're just a couple minutes off. One of the things that I had a few observations, but they're probably better deferred for any concluding comments or observations from Cody or Jason. Anything? Any final points you'd like to make?
Oh, I've just got one that I didn't get to that I made a note during Alex and Jason's thing about solar and storage. So right now, you probably noticed all of our stuff was standalone battery storage, and it really is storage as a peaker, storage instead of a gas turbine in a somewhat urban area. And lots of the storage that's getting built elsewhere is solar and storage. I would argue that that is almost entirely motivated by the current investment tax credit rules, which at 30% of CapEx is a big distortion in the price signal that tells developers where to put their capacity investments. And potentially that changes a lot with a storage ITC that kind of levels the playing field and just sends, I would guess, more storage to be closer to the load rather than out in the desert at a lot of these solar facilities. But I thought that was an interesting discussion that Alex and Jason both touched on in their notes.
I'll just add, yes, the prospects of storage will change potentially quite dramatically depending on which direction Congress decides to go with pending legislation. So stay tuned. This conversation in just a few months could be quite different.
One of the things we've been trying to understand better are how the relationships between storage and some of the both renewable and the conventional plants, like which ones have engaged in either through a DC coupling if you're on the same facility, but also firming up neighboring facilities, or maybe not even neighboring facilities, but just facilities that you're capable because of your electrical availability. You can firm up. Maybe they're not right next door, but they're on the same line. That might be an interesting development. This is more of an internal discussions we're having. What can we do to help improve our coverage of that, data coverage of that? And we're trying to give that some thought. So we encourage feedback to help us, particularly if it's viewed that is going to be an important area of development. We want to make sure we're providing data support for those considerations. Okay, it's 2:30. Timed it pretty well. That's not bad. We had scheduled a 15-minute break for people to get some coffee or take a break. And when we come back, Chris Namovich will host the next panel. Want to appreciate, very informative. I learned a lot. Cody, Jason, appreciate y'all taking the time to help us understand this issue much better. Appreciate your engagement regarding the questions. And with that, Tricia, do you want to give us some guidance, or should we just check back at 2:45 to hear Chris and his interesting panelists?
Yep, Glenn, that sounds good. I'll put up a slide that just lets everybody know that we're going to take a break, and we expect to hear from Chris just about 2:45 when he's ready to start panel 2.
Great, thank you.
Okay, I guess it's the time we said we'd reconvene.
This sounds good.
So my name is Chris Namovich. I'm the team lead for long-term electricity, coal, and renewables modeling at EIA. I'm in charge of the group that develops projections in these markets for EIA's annual energy outlook and international energy outlook products. Thus far in this session, or in this program, we've been focused on the data, where batteries are now, and we got a lot of good insight from the previous panelists on an idea of where batteries are going over the next few years. My job is to look out over a 10, a 20, or even a 30-year time horizon, so a little bit further out than the time horizon discussed in the last session. As many of you know, our annual energy outlook reference case is a projection based on current laws and policies. We last published this in January of the current year, so it doesn't account for things like the latest infrastructure bill or even many of the other laws or policy changes that were actually enacted over the past 12-month period, let alone a lot of the discussion that has occurred that is not necessarily binding federal or international policy. Much of the focus over the long term over the last years has been on policies that really could totally change the complexion of the grid by reducing or eliminating conventional, i.e. fossil sources of generation, and increasing intermittent or variable resources like wind or solar. I do want to note that even without these policies in place, and again, they're not incorporated in our model because they're not actually in place, we are already projecting a significant expansion of these resources, especially solar, but also wind. And as we see in our projections, this continues to create significant growth opportunities for battery storage over the next couple of decades. So that being said, this session will focus on this future period. We're going to get a deeper dive into EIA's own projections, a view from the National Energy Laboratory about some of their long-term projections and modeling of batteries. And we'll also get some on-the-ground insight from the California ISO, which, as we saw in the previous panel, is the ground zero for both the renewables revolution and the storage revolution that we're starting to see across the U.S. and even the world grid. So first up, I'd like to introduce Vic Linga. Vic joined EIA about 3 years ago and quickly took his assigned role as the energy storage expert on the electricity, coal, and renewables team. Although it was just the renewables team back then. In this role, he not only researches storage technologies and markets, but also maintains EIA's new Restore model, which was designed to help us answer the critical questions about wind, solar, and storage resources on the grid going through our 2050 projection horizon. As if that isn't enough of a job responsibility, Vic is also our resident geothermal expert on international renewable energy policy, and is also currently working on developing a new model to evaluate the use of hydrogen as a seasonal storage option in the electric power sector. And with that, I will turn the floor over to Vic.
Thanks, Chris. Yeah, go ahead and share my screen here. Can you guys see the screen okay?
Yep. Well, no, we just see you.
Oh, you don't see the screen yet?
I don't.
See, okay, I got it now. 1 second. See where Alex was confused earlier. Okay.
Yeah, it's starting. Yeah, you got it. But it's your home. There you go.
Okay. Alrighty, we'll get started because I'm gonna be going through a lot of information here. I'm gonna go through a little bit quickly, but please, if you have questions during the Q&A session or even during the presentation, I'll put them in the Q&A box about any of the items I discuss. We look forward to having a great discussion. So I'm gonna be talking about EIA's annual energy outlook from 2021. It came out in January this year. And the battery storage projections from that study. So yeah, I'll start off talking about the AEO, specifically the battery costs and assumptions to start off with, some of the results and our conclusions. So first off, the annual energy outlook. It's our annual study by EIA of the long-term projections of the energy sector domestically. We also do the IEO, which is our international energy outlook. The special thing about the AEO, in my opinion, is its coverage of the entire energy economy, not just the electric power sector, but the transportation sector, oil and gas, from the supply side, the demand sectors, from commercial buildings, residential, industrial, Each of these are modeled separately and in a lot of detail. About Teams. Apologize for that. Yeah, so the NEMS is AEO is an entire energy economy model that covers all the different sectors and our study. And then the model for that we use to generate the results for AEO is called NEMS, the National Energy Modeling System. And I'll be talking a little bit about it here. So I don't want to dive too deep into kind of the model mechanics of how NEMS works. I'm going to be talking more about the results for this presentation, but I think it's just important to outline here what I just previously said, in that it covers, it touches every part of the energy economy, and a lot of those sectors are modeled individually by separate teams here at EIA. We have a large supporting cast that really does a lot of great work to represent the domestic energy economy in a lot of detail. That being said, one thing to note, if you're trying to compare the kind of electricity, the power sector results from our model compared to other models, we'll have more maybe feedback from these other sectors because of our high kind of definition of modeling all the energy economy. But that kind of limits to some sense how detailed we can get in our own model for each of these models, specifically talking about the power sector, because of runtimes and processing power, and just when you're modeling so many things, you can't really get as detailed in each one. And I'll talk a little bit about that going forward. So there's advantages and disadvantages between doing an entire energy model versus kind of maybe a one sector model that's maybe not integrated with all the other sectors. I just want to point that out. So talking about the AEO, we run 9 cases annually. Chris mentioned the reference case, which is our baseline case of, you could call it our best estimate of what might happen in the future, but only with current policies. We don't change any policies that have been that are in law right now, and we don't include any policies that might come that haven't been written into law. Our other cases are the high-low renewable cost case. In the low renewable cost case, the costs for renewables, including storage, are 40% lower than the reference case. In the high renewables cost case, there is no cost decline throughout the projection period for renewables. They just stay the same as they were in 2020. In the high oil and gas supply case, we vary production costs and the resource availability for oil and natural gas. The low and high economic growth case, we vary the GDP growth from 1.6% in the low economic growth case to 2.6% in the high economic growth case. It's 2.1% in the reference case. And for the high and low oil price case, it's a similar kind of variation. The oil price at the end of the projection period is at $48 per barrel in the low oil price case and $173 per barrel in the high oil price case. So you can see here how varying these kind of inputs and model parameters has an effect on the amount of storage deployed in our different cases. In our reference case, there's about 60 gigawatts of total storage deployed through 2050. And this is similar to a lot of the other cases, except when you look at the low oil and gas supply case, which has lower natural gas prices than the reference case, and the low renewables cost case, where you see, obviously, when you reduce storage costs and also renewables costs, you get almost 160 gigawatts of deployment in this study. Moving forward, we're going to focus on the reference case, the low oil and gas supply case, and the low renewables cost case, just because of the variation in results. If we were comparing all these other cases to the reference case, you would see slight variations, but they would kind of be similar to the reference case. So that's why moving forward, we're going to kind of focus on the reference, low oil and gas supply case, and low renewables cost case. If you're interested in the results from the other cases, you can access all the data from our Annual Energy Outlook 2021 on our website. And I can answer more questions about those cases in the Q&A if people have questions about that. Talking specifically about battery storage assumptions in NEMS, we have two technology options: a standalone battery energy storage system. We only model a 4-hour battery, and we assume that it's the same amount of time to charge and discharge. And the round trip efficiency for that system is 85%. So you basically you discharge 85% of whatever you charge from the grid. And then we also model a PV hybrid battery system. Basically, for every 50 megawatts of battery that's installed, you install 150 megawatts of PV, and those are connected to each other so that battery can only charge from that PV. It doesn't have to be in those increments. It's just basically a 3-to-1 ratio. So if you install like 1 megawatt of hybrid battery, it'll install 3 megawatts of PV, and so on and so on. That system is inverter limited at the PV capacity. So for example, if you install 150 megawatts of hybrid PV, and then there's 50 megawatts of battery attached to it, the inverter will be that whole system will not be dispatched at 200 megawatts. It'll be dispatched at 150 megawatts, but with higher capacity factors at certain time periods because of the battery's ability to shift the PV generation. So yeah, in real life, obviously there's different systems, and I'll talk a little bit later about kind of like why we chose this to start off with, and kind of maybe what options going forward in the future could be for modeling it this in different ways. But this is how it is right now. This is how it's input into our model. Both of these systems can serve two applications. One is energy arbitrage, which is shifting energy from high-priced times, which usually when you have from low-priced times when you have high supply and low demand hours, to low supply hours when the price is higher, and then you can make money off of that, and also to meet reserve margin requirements. Those are the two applications that are meant by battery storage in our model. We don't currently include other applications such as frequency regulation and spinning reserves and other ancillary services in our model at this time. We're looking into that, but this is currently how we model the applications for energy storage. Talking about our other assumptions, our cost assumptions, we had a contractor in 2019 perform a cost analysis study to see how much these systems would cost, at the beginning of our projection period. Came out to $1,391 per kilowatt and $348 per kilowatt hour for the standard standalone 50 megawatt 4-hour system. And the PV hybrid system was $1,783 per kilowatt. And again, that's even though there's 200 megawatts in that system, its model is a 150 megawatt system because it's limited at the inverter. Just comparing this to prices from our historical data that Alex kind of went through earlier, from our 2019 Form 860 data survey. We see that out of like 45 plants that were over 2 hours in duration that gave us their kind of cost information, they had a little bit higher costs than we're modeling. This could be because of the small sample size and kind of some outliers that had really high costs. But I think our initial costs are on par with what other modelers in the space are doing. Now, moving on to the results. Basically, in our reference case, obviously, you see a lot of growth of renewables throughout the projection period. In 2050, it goes from 21% in 2020 to 42% share of renewables on the U.S. power grid. The actual share of natural gas, the amount of natural gas increases, but the share decreases to 36% from 40%, and you have a lot of retiring nuclear and coal. In terms of which renewables are growing the most, it's definitely solar. You see a lot of wind growth at the beginning of the projection period, and then it kind of levels off as solar costs continue to decline, among other reasons. Not much growth in other renewables such as hydro, geothermal, and biomass. Now moving on to projections for battery storage. We'll spend a little more time on this slide because there is a lot of information here. Let's just start with the reference case, the first row on this slide. You see there's a lot of battery storage deployment in 2050 in California. You see it's darker there on the first pink map, and then also in Texas, which is in line with what we're hearing with current builds. You don't see much in the kind of west region other than California. As you can see from the green wind map on the reference case, there's a lot of wind builds over there and a lot of natural gas capacity, combined cycle and CT plants serving that region. There's also a decent amount of solar in kind of like the CERC southeast region above Florida and the Carolinas. And it seems there's a lot of natural gas competing to kind of in that same area as well. And then there's kind of storage spread throughout kind of the Midwest and the Northeast to some extent in the reference case. Now looking at the low renewables cost and low oil and gas supply case, definitely you see a change in the, let's first look at the low renewables cost case. You see more storage in California and Texas, but you see a lot more storage in that southeast region I mentioned. It's really dark there. Maybe that could be correlating with the PV builds that had previously been mentioned. For whatever reason, in the reference case, it wasn't building that strong, but now once you lower the cost of storage, it competes strongly in that region. Outside of Texas and California, that's pretty much the strongest region we see growth in there, and we're going to dive a little bit more into that later. And speaking on the low oil and gas supply case, kind of the same pattern here. In that case, your natural gas prices are increased. You can see on the brown map, it's basically a lot darker all over the place. And then storage is kind of making up for some of that load. And also you can see there's less coal retirements because of the higher natural gas prices. In this case, it wasn't clear. The battery storage on the this slide is capacity, whereas the other four maps, solar, wind, and oil, natural gas, and coal, nuclear are generation. Like a lot of information here. We could talk more about what's going on, but we'll move on if anyone has any questions later and wants to go back to this. So the cost for battery storage declined throughout the projection period. This is due to some of the kind of learning by doing that Jason mentioned earlier in his presentation. I kind of told you guys about the initial costs by the Sargent Lundy report, starting for standalone battery storage over there, the red line around 1,200 in the reference case, and coming down to 600, a little below 600 by the end of the projection period. You can also see the solar hybrid cost comes down quite a bit. This is the cost before any tax credit is applied, obviously. So it goes down from about 1,600 to 800, nearly cutting in half. In the low renewables cost case, as we said, the constraint in that case is to lower costs 40% more than the reference case. So that was kind of forced in there for that case for this for these technologies. And then a low oil and gas supply case, you see kind of similar cost declines to the reference case technologies. Okay, now talking about standalone versus PV hybrid, the two storage technologies that we model in for the AEO. It's pretty interesting looking at the different cases and the way they're deployed. Again, I'll just quickly mention what Cody was alluding to earlier. A strong driver for these PV builds is the investment tax credit. When I guess basically these that storage plus PV is able to take advantage of higher priced hours when it sells the electricity, and also the PV can charge the on-site storage instead of generating when it wouldn't make that much money in low priced hours, for example, the middle of the day. And then but you also lower their capital costs because of the investment tax credit. So you're able to make more money from operation, as well as lower your costs, which is a strong driver for growth for the PV hybrid, which is the light pink on these graphs. The standalone storage actually doesn't get deployed too much in the reference case. A decent amount of those builds are planned builds at the beginning. So definitely PV hybrid, and we'll get more into that on the next slide. But a key takeaway from this slide is you can see when you look at the side cases, in a low oil and gas supply case, you actually do see a lot of standalone storage deployed, even though it's not getting the ITC, and you haven't kind of forced down costs as you do in the low renewables cost case. In low renewables cost case, you see both the PV storage hybrid and standalone storage get deployed because their costs have been lower. But yeah, the interesting result here is the low oil and gas supply case, which we can like dive a little bit more into, going back to our heat maps here. So in the reference case, the first graph there is the same graph we looked at before, but now we're going to be splitting it up into standalone and hybrid. So you could see that a lot of the standalone battery or a lot of the battery storage that was in California was standalone actually, and then a lot of the battery storage that was in Texas was PV hybrid in the reference case. So it's interesting to see how different regions, in our model, prefer to build one or the other technology. Seeing that trade-off in higher initial capital costs for the PV storage hybrid, but being able to take advantage of the tax credit and giving up flexibility that the standalone storage has when it can charge and discharge whenever it wants, pretty much, not just based on when the PV is shining. Moving on to the low renewables cost case. Again, California has a decent amount of the storage deployed in California is the standalone battery storage, but also there's some hybrid storage that's part of that. Again, Texas is all the hybrid storage, pretty much, not much standalone built there. There is some, I'm talking relative terms here. And then another interesting phenomenon is that southeast region we had mentioned. You can kind of see it, a lot of storage is deployed in that southeast region, and a lot of it is standalone battery storage and not PV hybrid. And again, we're going to dive even deeper into that here soon. You kind of see similar patterns in the low oil and gas supply case. I know there's a lot of information. Please, if anything is confusing or you want anything clarified further, put some questions in the Q&A box and we'll definitely get to them. Spending a little extra time on some of these slides so people can kind of process them as I go through. Okay, now moving on to actually seeing the hourly dispatch by month in one of these regions. So you see here, this is for California, basically the entire state. In 2022, which is basically pretty close to the beginning of the projection period, you see kind of higher loads in the summer, also higher solar supply in those times, and you see kind of the interesting thing to look here is the pink and the gray that's at the bottom of these graphs. The pink is pump storage, and the gray is the battery storage. That's the standalone battery storage for the gray. So you can see that most of the kind of arbitrage that's happening here is that pump storage. You can see in the 2022 in the reference case, which is pretty similar to 2022 in the low renewables cost case because it's so early in the projection period. But you can see the pump storage is charging in the middle of the day in most months, and is dispatching kind of in the afternoon to evening hours afterwards. And this pump storage has been around for years. It's doing this today. It's been doing it for the last few years. So there's the pump storage in California, but you can see how this changes when we move out to 2050 in both the reference case and the low renewables cost case. You could see that that gray bump underneath the pink at the bottom, that's the battery storage performing the same arbitrage, but to a greater magnitude, even in the reference case in this region. And it's basically taking advantage of the curtailment, which is the brown, kind of dark brown bar at the top. There's still a lot of curtailment that's not being used to charge the batteries, but a decent amount of it is being used that would otherwise have been wasted energy in order to charge these batteries at low cost and dispatch them at later hours when you might have had a larger kind of that blue color there, which is a gas combined cycle or oil and gas peakers in this region. And moving down to the low renewables cost case, you just see way more curtailment, especially in the April through June months, even March. And then you can see in those months kind of a lot of battery storage and pump storage being used, and then kind of taking away from that natural gas peakers that might have been there as well. Now moving on to a completely different region that we've talked about a little bit. This is the southeast region. You can see there's a lot of more coal and nuclear in this region. A decent amount of it, especially the coal, gets retired looking out to 2050. You still see those higher loads in the summer months. But what's interesting here is you have almost no solar in 2022, and a lot more gets built in both the reference case and the low renewables cost case, throughout the projection period, where you're having it, sometimes being like meeting half your entire load in some hours in some months. Actually, most months have that phenomenon. So yeah, you can see here also you have the pump storage in the reference case. Not much storage deployed in the reference case here, standalone storage, but you do see some solar hybrid storage kind of deployed there. You can see that's kind of like the darker yellow underneath the big yellow. But then when you, in the low renewables cost case, you see a lot more storage deployed. It's all standalone storage, and it's kind of meeting these high solar penetration times during the day. That you can see kind of the differences between this region and the last one, kind of when you can kind of see the effect of coal retirements and how that new load is met through kind of PV and standalone storage. Yeah. Oh, another big difference between this region and the last one is there's almost no curtailments here. The storage is somehow used much more effectively, or maybe there's the time, maybe the load patterns in this region kind of correlate to when the sun rises. But for whatever reason, there's a lot less curtailments in this region than than California ISO. But also California ISO had a much larger percentage of its total load as solar, but it's still interesting to see.
Vic, we're starting to run a little bit low on time here. Oh, you're on your conclusions. Never mind.
Yeah, I'm good, right? I got 3 minutes. Taking questions at the end. Right, so just main conclusions from kind of looking through the data for today's presentation. In all scenarios, there's going to be a large growth of battery storage over the next 30 years compared to what we have today. It was mentioned before by Glenn, storage was set to double just this year. So, but just trying to understand how much it's going to grow and where it's going to grow first, as opposed to other places, and why is kind of some of the things we looked at today. California and Texas, as is shown in just if you look at historical data today and planned data for the next couple of years, they continue their ongoing investments throughout the projection period for energy storage. And in some scenarios, you also see a lot of investment in the MISO and CERC regions for battery storage. Lowering technology costs in the low renewables cost case increase the deployment throughout the USA. There's pretty kind of everywhere you saw more battery storage, but increasing gas prices in the low oil and gas supply case was more kind of selective into where the storage got deployed. So that was interesting to see. And kind of like I mentioned at the beginning, we only model a couple of technologies. We model 4-hour duration batteries. So there are things we can do to kind of improve our modeling to get even more information out of this. If anyone wants to look at my slides later, here is the contact information of me and some other members of my team who work on these topics. And there'll be some links to a lot of our resources. And I guess we'll take questions at the end.
Thanks, Vic. So next up, I'm going to introduce Will Frazier. Will is a member of the Economics and Forecasting Group in the Grid and Planning Analysis Center at the National Renewable Energy Laboratory, or NREL. He is a part of the team that manages and operates the Regional Energy Deployment Development System. It used to be deployment, didn't it? Or REEDS model. NREL's primary tool. This is NREL's primary tool for modeling long-term changes of large-scale electricity grids. Will's work primarily focuses on representing resource adequacy of variable generators and storage systems. Will has a master's degree in material science and engineering from the University of Colorado, Boulder, and a bachelor's in physics from the University of Nevada, Reno. In his spare time, he enjoys rock climbing and chess. And if you're ready, Will, go ahead and take it away.
Sure thing, Chris. Can you hear me?
Yep.
Great. All right. I will be speaking today about some results from our storage future study. So we can go to the next slide here. Please. Okay. So about the storage future study, it's been a multi-year effort involving several people here at the lab to characterize the rapidly increasing role of storage that we expect in the electricity sector through 2050. This includes a large handful of publications, including some less analysis and more narrative-focused pieces that I would recommend people check out if they don't have a lot of experience with storage. Those being this 4 phases report, which kind of lays out a framework for the expected evolution of storage in the electricity sector that we think will happen at NREL. And also most recently, a paper on the challenge of defining long duration, what we mean when we say long duration storage, so that we can, try and get everybody on the same page. I think multiple times throughout the workshop today, we've had people say things like short duration or long duration, and rightly so, clarifying questions have come up, meaning like, so what exactly do you mean when you say short duration? What do you mean when you say long duration? We also have several analyses published on distributed resources, operational changes in systems that have high amounts of storage, and then today I'll be talking about a report that goes through several scenarios for cost-driven storage deployment in the grid through 2050. And before I start, I'll just, our one key conclusion is that under all scenarios, we see dramatic growth of storage in all scenarios. So we can go to the next slide here. Just quickly talking about the sensitivities that we looked at in this study. So we ran a total of 19 scenarios, and this included varying the assumptions for costs of renewable energy, of storage, of future natural gas prices, and also for transmission, and some combinatorial scenarios of these as well. So we can go on to the next slide, please. Just some real quick, a few notes on the improvements that we've made to the REEDS model so that we could do this study. First of all, we're using 7 years of weather and load data for analyzing system reliability, whereas previously we were using a single year of hourly time series load and weather data. We also have our storage resources split out by duration, and this allows us to capture the relationship between storage duration, capacity provision, energy arbitrage, and cost. We also include ancillary services, but as was covered extensively in the first part of this workshop, once you have a large amount of storage on the system, it tends to swamp those markets and reduces the value that storage can get from those. So we do have that included, but I don't talk on it much in this presentation here because it generally doesn't provide as much of a market share as capacity or energy arbitrage do. Lastly, we now have an hourly dispatch of generation, storage, and transmission for each hour of the year, and this is used to inform investment making decisions within the actual optimization of the capacity expansion model. And then here are some examples from some dispatches and a few key days. We can go to the next slide. So our modeled storage deployment in the storage feature study. So on the left, I have the cumulative storage deployment through 2050 in the reference case. And again, this is split out by duration. So we have 2, 4, 6, 8, and 10-hour batteries. And we also have pumped hydro within the model. All pumped hydro is assumed to have 12 hours of duration. We start with about 23 gigawatts of pumped hydro in 2020, and moving forward, we see a little more than 200 gigawatts of storage deployed by 2050 in our reference case. And one important thing to note here is that we see most deployment starts with our shorter duration resources, so starting with 2 hours and moving into 4 and 6 and 8 hour resources as the potential for these shorter duration resources to serve peak demand is saturated. We tend to see longer durations deployed over time, and I'll talk a little bit more about that later on. And on our right, across all of our resource sensitivity scenarios, we see significant amounts of deployment. Even in our high battery cost case, we see about 150 gigawatts deployed by 2050, although most of that deployment in that scenario is deferred to after 2040 or so. But suffice to say that we expect to see a lot of energy storage deployment. And I will also note here, I forgot to mention earlier, that we are using lithium-ion battery cost projections in all of these scenarios. As was discussed earlier, this is the technology that's at the forefront and is cost-effective today. The modeling work that's done here is mostly technology agnostic, so were there to be any other sort of technology that comes along and can match the cost and performance metrics that we assumed for lithium-ion batteries in this study, you can feel free to substitute in whatever technology that may break through in the coming years and decades. So with that, we can go to the next slide. So all of this has to do with the duck curve. As we talked about previously, when you have lots of PV generating in the middle of the day, it shifts your peak demand to the night. It kind of narrows that peak demand as well, and it really creates a huge opportunity for diurnal storage to play an important role. So in this graph here, we're looking at our simulated load profile in California in 2050. So this is in CAISO. And I'm also showing the net load profile for the low PV cost and the low wind cost cases. So this is load net of wind and PV production. And the yellow line there, the low PV cost scenario, has huge discrepancies between where net load is during the middle of the day when the sun is shining and where it gets up to in the evening after the sun goes down. And that creates a lot of opportunity for storage to shift the energy there, both for providing capacity value and also for optimizing energy generation such that we're using the least cost resource suite that we can. So our energy price profiles, as we've seen before in previous presentations, the energy price profiles tend to follow pretty closely along these net load profiles. So not only is PV increasing your ability for storage to provide peak demand, but it's also increasing the value that storage can get from arbitrage due to the price volatility associated with these large swings in net load. So we can go to the next slide. We have some scatter plots here quantifying some results from that. So based on those net load curves on the left, we have, we're plotting the peaking capacity potential. So this is the potential for storage to serve peak demand, and this is storage up to 12 hours in duration, as determined by the shape of these net load profiles. And we have plotted that against the PV penetration in each of these regions, in each of these scenarios. And we see a clear correlation between increased PV generation and increased ability for storage to provide peak demand. So relative to today's levels, once you get up to about 40% PV penetration, the amount of storage that can provide diurnal peak shifting roughly doubles. And on the right, this is quantifying the energy time shifting potential of storage over the course of the year. So this is as determined by the energy price profiles that come out of our hourly dispatch. And again, when you have more PV, when PV is generating a greater share of your energy, you see greater price volatility and then a greater potential for storage to take advantage of energy arbitrage. So in both senses of providing capacity and energy arbitrage, PV plays a huge role in increasing the potential for storage and increasing the value that you can see from storage providing these services. We can go to the next slide. there was some talk earlier about wind and whether or not there are similar correlations between between wind and storage as there are between PV and storage. It was said earlier that the correlation between wind and storage is really not clear, and my results here on the slide are going to reiterate that. So what we're looking at here is the amount of generation that is used to charge storage. So this, you can think of this as another way to characterize the utilization factor of storage. So we're not looking at the we're not looking at the gross output, we're looking at the gross input to storage, which essentially is the same thing minus the round trip efficiency losses. And we've plotted that against the PV penetration and the wind penetration. So the little blue dots are regional results from our model, and then the national aggregate results are plotted in yellow for each of our scenarios. And as we can see, there's a huge, an obvious correlation between the utilization factor of storage and the amount of PV penetration. Whereas with wind on the right, the situation is far less clear, and there are certain areas of the country with very high PV penetrations and almost no wind deployment that have very high utilization factors of storage, which tend to throw off any sort of correlation that you can attempt to draw here. We can go forward one slide. With that in mind, I will say that we have seen that transmission correlates much more with wind. So one goal that we had in this study was to understand what sort of competition, if any, exists between storage and transmission. And what we found that there wasn't any strong competition directly between storage and transmission per se. But what we did find is that PV tends to drive storage deployment, whereas wind tends to drive transmission expansion. And when you think about it, it kind of makes sense that PV is going to benefit from spatial or from temporal flexibility, whereas wind is going to benefit from temporal flexibility. So what we have here is in the top left, the battery capacity, top right is transmission capacity, and the bottom left is PV, and the bottom right is wind. So if we look at the red line, that's our low wind cost scenario, and you can see in the bottom right that leads to about double the amount of wind capacity in 2050 relative to the reference case. And we also see a significant amount of transmission expansion in that scenario. And the orange line, the low PV cost scenario, we see significantly more PV deployment, and we also see significantly more storage deployment relative to the reference case. Really what we're seeing, I would just reiterate one more time, is not direct competition between storage and transmission per se. Really, it's a second order thing. Really, it's a matter of what resources are providing your actual electricity, and what sorts of sources of flexibility can be advantageous for those resources, and integrating those into the greater power system. I have a couple more slides, so let's try and get through these while we still have some time. So here we tried to tease out from the model the relative value of the different services storage can provide. So the three services that storage can provide within our model are providing firm capacity, providing energy time shifting, and also providing operating reserves. What we did was we ran the model, and in each case restricted the ability of storage to provide that service. So the dashed line here, storage can provide all services. The yellow line under each battery cost assumption Storage can't provide operating reserves, and that really doesn't make a difference in storage deployment across these scenarios because as we've said before, the market size for storage is much greater for these lower margin opportunities, which tend to dominate when you're looking at storage projections out through 2050. We did find that providing firm capacity was the strongest driver for storage deployment, although the combination of providing capacity and shipping energy in time is what allowed for optimal storage deployment for the model to reach optimal storage deployment in these scenarios. So we can go to the next slide. There is one last slide here, and there's kind of a lot going on here, so I want to spend a couple of minutes on it. And basically, if you don't take anything else away from the slide, it's summarized in that blue box on the right there quite nicely. And really all I'm saying here is that storage is optimized based on the relationship between capacity value, energy value, storage duration, and storage cost and performance, right? So we have these competing factors where storage cost increases with duration, right? If you want to build a 2-hour battery versus a 10-hour battery, the 10-hour battery is going to cost more because you have to, include more battery packs in your system. The cost on a per kilowatt hour decreases with longer durations of storage, but the nominal value of a 1 megawatt 2-hour system and a 1 megawatt 10-hour system is going to be higher for the longer duration system. You're also going to get more energy value from longer durations of storage, although that tends to increase and then level off. As you can expect, storage behaving throughout the day, charging from low price hours and discharging in high price hours. You only need a 2 to 4 hour device to get most of that value, whereas if your storage devices are charging and discharging for longer, those marginal hours are going to have less volatility because, ideally you're already working with the highest volatility hours first. And for capacity value increases as your duration goes up, but only to a point, because once your storage duration is long enough to serve peak demand, then there's no additional marginal value for increasing storage duration. So in this plot here, on the left for each of these scenarios, I have the peaking capacity potential. So this is the ability for storage of different durations to serve peak demand based on the shape of the net load profile as we looked at before. And on the right is the actual realized optimal deployment within the model. So as you can see in our reference case, the optimal economic deployment of storage closely aligns with the durations that are required for storage to provide peaking capacity. And looking across the subset of scenarios that I've included here, we see that the peaking potential for storage varies quite a bit from one scenario to the other, and that is because of the different PV penetrations that we have in these scenarios. So in our low PV cost scenario, we have 43% PV penetration relative to 29% in the reference case, and there is the potential for an additional 50 gigawatts of storage to receive capacity credit and provide peaking capacity. The low end cost scenario has less, and so on. So that is one piece here. The other piece is the durations that are deployed can vary. So in particular, if you look at this high natural gas price scenario, we see that the model transitions from 4-hour storage to 6-hour storage sooner than it otherwise would have needed to provide peaking capacity. So the model is investing in more energy storage than is necessary to provide peaking capacity, and that is because the high natural gas prices in this scenario lead to greater our energy arbitrage potential. And so that energy arbitrage potential actually drives some of that additional energy storage deployment in this scenario relative to the reference case. And in our low battery cost scenario, battery costs come down to such an extent that it's advantageous for the model to deploy more shorter duration resources so that it can take advantage of the highest and lowest price hours for charging and discharging respectively. So I have one quick summary slide, and then we can end my presentation and move on to the next one. So just to reiterate, capacity value and energy arbitrage, the combination of the two drive storage deployment. That's where the big markets are over the next several decades. Diurnal storage is much more synergistic with PV than with wind. We see significant growth across all scenarios, greater than 125 gigawatts of battery deployment, even in our high-cost battery scenario. And once again, any storage technology that can meet these cost and performance metrics would be competitive based on the results of this paper. This isn't necessarily limited to lithium-ion batteries, although it's been the primary focus of every presentation for very good economic reasons up to this point. So thanks again, Chris and EIA, for having me. We'll defer questions to after the next presentation so that we all have time to speak. Thank you so much.
Thank you, Will. Very interesting presentation. Before I get on to the next speaker, I'd just like to remind folks in the audience to please type your questions for Vic and Will, and as our next speaker is speaking, into the question box so that we can address those after the presentations are over. So finally, it's my pleasure to introduce Gabe Murtaugh. Gabe has 10 years of electricity industry experience and is currently as a storage sector manager at California Independent System Operator. Gabe oversees storage-related policy, including policy related to developing and improving the storage model and policy related to hybrid and co-located resources. He also serves as the liaison for storage-related issues for parties outside of the ISO. Gabe has experience developing policy for resource adequacy and backstop procurement for CAISO. Previously, Gabe held roles in the market monitoring group at CAISO and as a market monitor for the Mid-Continent ISO. Gabe holds a master's degree in economics and an undergraduate degree in computer science and engineering. And without further ado, Gabe, if you're ready to take the stage, it's yours.
I am, Chris. I am trying to get my webcam going, and it doesn't seem to like me very much. We're going to have to push forward without it for now. I'll continue to try to work on it. So I apologize for that. It certainly is a pleasure to be here today, and I'd like to thank you for inviting me and thank the participants who are online listening to this, and give a special shout out to Vic and Tricia for managing things behind the scenes. I think they've done a great job, and I appreciate that. Having plenty of experience leading meetings here at the ISO, I can appreciate what a chore it is. So thank you guys very much for being here today. I would say that the earlier discussions and the panelists who presented before me have really been outstanding, and I think they've already hit on a lot of the things that I'd like to talk about. And, I may sprinkle in a little bit of additional color on some of what they were saying while I'm going through my slides. And I realize I think we have a hard cutoff in about 30 minutes from now, so I'll try to move quickly. So, Tricia, if we could go on to my first slide, I think that would be great. I did want to give, and I think this is appropriate, just a little bit of a picture about where California ISO today is and, where it is we've come from and what we're moving towards. So, for those who don't know, the California system is a summer peaking system, and we peak between 45 and 50,000 megawatts during that period. And about a year ago, we had as little as probably 500 megawatts of storage. Today, we have something like just under 2,100 megawatts of storage, so more than 2,000 megawatts, which for a system of our size is a pretty substantial change. And I think looking at the data that was presented earlier, this might, the amount of capacity that we have on the system right now might break some of the scales on those graphs that we were looking at for installed capacity across the entire country, let alone just thinking about California. So it's been, we've experienced some pretty tremendous growth in the last year. And I think as everybody has said, there's no signs that that growth is going to be stopping anytime soon. So we fully intend that things are going to keep moving at a very, very rapid clip into the next few years. A little bit more color here, and I think this has been covered as well, but nearly all of the storage in the California ISO system is 4-hour duration batteries, and nearly all of that capacity is lithium ion. The reason that developers here in California develop 4-hour batteries are explicitly because that's what you can use to count for resource adequacy capacity. So in the California markets, a 4-hour battery, and this is the way that they're structured today, and there's a number of talks going on about how it may change going forward. But today, a 4-hour battery that can provide 100 megawatts counts as the same amount of resource adequacy capacity as an 8-hour battery, as a 10-hour battery, as a 100-hour battery. So obviously, for those reasons that Will was just talking about, 4 hours, if you're getting the same amount of compensation through your resource adequacy capacity payment, which in California is the primary way that resources make revenues, you would elect a 4-hour resource. Of course, 2-hour resource or a 1-hour resource wouldn't count. For a 2-hour resource, you can only count for half as much capacity, and a 1-hour resource would only count for a quarter of the generating capacity of the resource. Also, this has been noted, so I think this is really a tribute to how nice of a set of presentations we've had already, but nearly all of the new capacity is coming in at either new solar facilities or existing solar facilities on the California ISO grid. So there are those synergies between locating storage resources with renewable resources, both wind and solar. Here in the state of California, though, solar is certainly more prolific than wind, and we are seeing that because of the economics of how our systems work and the duck curve, which was pointed out earlier, prices are lowest during the times of the day when solar is online here in California. That's true all 4 quarters of the year. That's when storage resources find the economic proposition of charging the greatest, and then they're saving that energy for later in the day after the sun sets, and you can discharge the energy then. Obviously, there are some synergies there. If you've already got interconnection set up for an existing solar facility and you add batteries onto that solar facility, you may not actually need to increase the interconnection limits and the actual physical hardware that sits on the interconnection, but you can also accommodate storage resources, which could be both profitable for resource adequacy purposes, but could also be profitable for energy arbitrage, buying energy low during those solar hours, selling energy later in the day. And in fact, that is what we're seeing storage resources on our system do. Just another note on that, I know we heard earlier in the presentation that there's a whole bevy of different products that storage resources might provide to the grid. And in California, it certainly was the case that, as recent as about a year ago, we saw storage resources primarily providing regulation services and other ancillary services to the ISO. Today, that really has changed. Most of the 2,000 megawatts of storage that we see on our grid today do participate in energy arbitrage, so they are moving that energy from low-priced hours to high-priced hours, and that's the primary function that they serve on the grid. But certainly they do have other roles while they're participating, and we still do see storage resources providing ancillary services. But obviously, as there's more storage developed and integrated onto the grid. It puts additional upward pressure on supply of ancillary services, and we see lower AS prices and less drive for those storage resources to participate in those markets because the revenues just aren't there to support that. And I would be surprised if we did see in future years across the entire U.S. footprint even more participation from storage resources in AS as we see deeper and deeper penetrations. I do think that more and more of the usage is going to be for this energy shifting, potentially for local reliability, potentially for substitution of transmission assets, those kinds of things, but unlikely that we'll see a ton more developed specifically to do ancillary service type products. Much of the additional procurement of storage is driven by state mandates. So here in California, we have the California Public Utilities Commission, and they have been driving the huge increase of storage that we've seen over the last year, and they will be continuing to drive additional growth of new resources on our system into the future. So they have a procurement target of 3,300 megawatts by 2023, and then they have another 11,500 procurement target by 2026. So if you sum those up, you're looking at more than 14,000, well, almost 15,000 megawatts of new capacity by 2026. Projections from the ISO and projections from other state entities, including the CPUC, indicate that most of that new capacity of those 15,000 megawatts is going to be primarily storage resources. Again, we might see some new growth in renewable generation, some new storage, some new solar, some new wind, but the primary capacity that's going to be coming online will be storage, and we would likely see a lot of that storage paired with existing solar or potentially some of the new solar that's coming online via these procurements. And frankly, I think that the story here in California is very similar to the stories that we would see unfolding in other states across the country as states set mandates for greenhouse gas reduction and changes in the makeup of how electricity is generated across the country that will drive new procurement. And all of the models show that that new procurement is going to be made up of storage resources, wind resources. Potentially here in California, we've got some geothermal, we've got some hydro resources. We're certainly going to be looking at synergies we can get from participating in broader markets and agreements with our neighbors. So the solar profile here in California is different than the solar profile of Arizona. So you can get some synergies from the sun rising earlier in Arizona and setting later in California, and potentially leverage that to make your system more reliable. Similarly, we know that there's wind in some of the western states. Wyoming has a large proliferation of wind and has plans for significant wind development. The questions are, how do we get that wind into the state of California? And then obviously there's a significant amount of hydro resources in the Pacific Northwest. How can we think about the best usage of that hydro, potentially not just in the Northwest or California, but across the entire western part of the United States? Storage does pose some challenges for grid operations, and I would say on a day-to-day basis, these are the kinds of things that I'm thinking about in my current role. Storage resources must be charged to provide energy to the grid. So when you're thinking about forward markets or the planning time horizon, you can sort of make these assumptions that, well, we know we need to charge up storage resources so that they're available during the peak hours of the day. So we're going to make that assumption, and then they'll be there and they can count for capacity, and we can work in sort of those questions that Will was trying to tackle about, what kind of duration batteries do we need, and how can we get the most efficient length of duration of battery. And it's really the challenge of the grid operator now to think about in the real-time time frame, where I might only be the markets that are dispatching the storage resources may only be looking ahead an hour or so how do we make sure that I have the right amount of state of charge in the right resources to be able to meet my peak load later? I would say today, the day-ahead market does a fairly good job of ensuring that we've got storage resources charging during the lowest price hours of the day and available for discharge during the hours when those storage resources would be critical. But once we get into the real-time time frame, things are a bit more tenuous, and we do have those shorter look-ahead windows, and things may not materialize at exactly the same way we outlined in the day-ahead market. Obviously, things can change, and as that happens, we need to make sure our grid and the tools that we have are agile enough to be able to handle those kinds of circumstances. We have similar kinds of issues that arise in the local areas as well. For local reliability, we may need to explicitly hold state of charge in particular batteries to ensure that in the event of a major line coming into that local area being lost or a generator inside of the local area being lost, we can still maintain reliability, keep the lights on in that local area via the storage resources and the capacity that we have from the storage resources. And that is, again, a different kind of problem than the ISO is used to solving. We're used to looking at local areas. We're used to thinking about reliability in those areas, but thinking about how much state of charge we need to have in those local areas is a little bit of a twist on sort of the traditional problems that we've solved around local areas. And then, you know, we get from the position where we're in today, where we have some small penetrations of storage. We are starting to see storage marginal in local areas. We do see storage marginal at the system level on the tightest days. But as penetration grows and we retire traditional resources, that will happen more and more frequently. So we need to continue to build and evolve those tools. But at the same time, we're also moving towards the future where we don't just need storage resources to move energy from, say, 11 o'clock in the morning to 6 o'clock at night. Now we start to need storage resources to hold energy for, you know, that 1 week period or the 2 week period where we don't have very much solar generation, perhaps because of extended periods of cloud cover. You know, we've got a bunch of cloudy days in a row. And at the same time, maybe we don't have very much wind generation just because of slack winds. So how do we get the right market incentives in place, and how do we even start thinking about the problem of multi-day needs for storage and ensuring that there's enough state of charge in those storage resources to be able to carry us through those periods? Lots of material on that slide. Thanks for bearing with me. Tricia, if we could advance to the next slide, please. This is a little bit of just a little bit of color on where we were in February of 2021 and sort of where we are today, mid-November of 2021. What's going to happen between November and December, and then finally what's going to happen into Q1 of 2022. This is data that we have in our database where we're actually tracking actual amount of installed capacity through our master file. So that has been registered with the ISO and is coming online imminently. So this data is actually very good, or a very good representation of what's on the system and what's about to be on the system imminently. It also, you know, I would note that some of these curves have been pushed out to the right a little bit because of delays in the supply chain due to COVID. You know, from talking with storage developers and folks who are out there actually building these projects, we do anticipate that most of these delays are going to be short-term, impacting this year and next year. But in the future, delivery for things, for say, development in late 2022, earlier 2023, things are looking to be on time and on budget. So that's really positive news for storage, and we do anticipate large growth in those years. So November, as I've already said, we have a little bit more than 2,000 megawatts of storage installed on our system. That's indicated by the orange bar there in November. In December, usually we get additional capacity ready to be online and get contracts for the 2022 RA year. So we're expecting about another jump of probably another 1,000 megawatts by the end of the year. And if it doesn't come in December, it likely will come in early Q1 2022, where we're going to see also a little bit more of a jump, maybe another 200 to 400 megawatts in Q1 of 2022. So it's really been a year, and we've heard this from all the other presenters, of rapid growth in storage here in California, and we're anticipating that to continue into the future. So, Tricia, if we could just go to the last slide. I've already hinted at a lot of this, and I'll go through it briefly at a relatively high level because I do want to get to some of the Q&A. I think that's where we can really have a lot of value added in this conversation. But just so everybody knows, California does have a goal to be greenhouse gas neutral from electricity generation by 2045. So it's a relatively aggressive goal. There have to be a lot of changes on our system in order to get from where we are today with the resource mix we have today to a grid that's reliable in 2045 and doesn't rely on greenhouse gas generation at the same time. And it could also involve, as we've heard from the other presenters, decarbonization and electrification of other industries, which could mean even more load, which means, of course, you need to build out even more renewable resources and storage resources to make the grid work. So the modeling, and I've already said this, but the modeling that we're anticipating are to make 2045 happen are a considerable amount of renewable resources paired with storage resources to kind of get us through those periods when the renewables just aren't generating or aren't generating enough to meet loads. And then specifically the key here in California, in addition to a huge amount of storage resources, it's also a fairly large dependence on solar generation. And I think, like I was hinting at, I think the solar generation is also going to be coupled with us partnering with neighboring states and seeing what they can provide to help California and what they can provide, likely in the way of solar generation and excess solar generation to those neighboring states to help them meet their greenhouse gas goals and their needs. One interesting thing is that the most challenging times of the system, I think the first thing I mentioned was that the California system today is a summer peaking system, meaning the most challenging times on our system today are in the summer. But when we shift towards 2045, we see those most challenging times shifting from the summer months to the winter months. And instead of being in the evening after solar goes down, the most challenging times are the hours immediately prior to sunrise, because those are the hours where you've already been relying on your storage fleet for multiple hours and you're the most likely to be depleted. And that's when we could find times where it's challenging to meet demands on our grid. And as I've already said, the multi-day, potentially multi-week instances where we see low solar generation and slack wind, which means slack wind generation for electricity, those are the periods when our storage resources are going to be tested the most, and we are going to need those tools in place to ensure that we have sufficient state of charge. And that's really a problem that we here at the ISO haven't addressed. But I think that's something that we're probably thinking about in a 5-year horizon to start, in earnest, the conversation on how we begin to tackle this. But frankly, I don't think that this is a question that's being addressed anywhere across any RTO or ISO. So it's really interesting work, and I think that will be a big part of what ISOs and RTOs are thinking about in the next few years. And we've heard this already, but long-duration storage will be necessary to operate that future grid. And we're not talking about 4-hour batteries versus 8-hour batteries. We're talking about 4-hour batteries, which is what we're installing and building today, versus something much larger than that, which could be as much as 100-hour duration batteries. It could be even larger than 100-hour duration batteries. So we need to think about what the right size is and where we can find that sweet spot in energy duration versus power duration. And I think that is a difficult question and not easily answered, but a lot of work will be done in that area as well. Likely, well, it says likely on the spreadsheet or the Excel here, but I think likely is not even a strong enough word. It's almost surely not going to be the lithium-ion batteries that we're installing on our system today that will be the technology that's dominating storage resources, at least for these longer duration projects in the future. We've already seen lithium-ion just within that technology type grow by leaps and bounds. There's a lot of other technologies that are out there with a lot of different chemistries that are emerging today. And we do, here in California, expect that probably one of those other technologies will start to take hold. And then similar to costs for lithium ion, we'll see costs start to decline for those kinds of technologies, and we'll start to see them being built more frequently. And, I don't want to go into any more specific details here, but we may require new market products and new methods for compensation once we have these resources on the grid. How do you get a 100 megawatt or 100-hour duration battery charged and ready for an event that may or may not happen, or may only happen 1 in 10 years, and have that in the state of charge and not doing anything else to earn market revenues, energy market revenues? Maybe you need a different product for that, or maybe this is something that's just covered in standard resource adequacy contracts or power purchase agreements or something like that. I do think it's a good question, and it's something we're going to need to think about, but it's definitely going to require market products to ensure that the resources are charged and available. So with that, Chris, I know that's tons of information, probably more than you wanted. Happy to turn it over to you for these last couple minutes to try to field a couple of questions.
Right. So I have a couple questions. I think I'm going to take my moderator's prerogative here and sort of meld a couple together along with one of my own. And to do that, I'm going to, if I can I share content here, Tricia? Doesn't seem to allow me to do that.
Give me 1 minute and I'll pass it to you. No problem.
Okay.
It should pop up on your screen.
While we're waiting for that, I was actually watching a presentation yesterday that talked about this 100-hour period or whatever it is where you don't have the wind or the sun, and it was from a German fellow, and the Germans now have a term for it called Dunkelflaut. So that's I like that term. It means basically dark calm or dark doldrums in German. So we talked a lot about two themes that came up a lot, both in this session and the previous session, which one is that the driver is solar, or one of the major drivers is solar. Wind is not so much a driver. Other things it plays, but the real driver appears to be solar. Batteries match well with solar. Storage matches well with solar. And then the other question that came up primarily in this presentation is sort of how big do batteries need to be duration-wise, 4 hours, 2 hours, 8 hours, whatever. And so one way of thinking about this, I put up a map from NREL, some of Bill's colleagues that they put out many years ago. I guess this one's actually updated for a couple of years ago, of what's called the GHI, Global Horizontal Irradiance of the U.S. And I want to draw your attention to the lower right corner, the numbers on the scale there, which range from 4 to 6, basically. And what that means in layman's term is that's the number of average hours over the year per day that you get sunlight. So somewhere between 4 and 6 hours, and obviously you get 12 hours of sunlight at some point, but that's really low light during the morning, low light in the evening, and high light during noon. So this is kind of like a capacity factor where you're just kind of compressing that all and assuming that it's all at maximum power for 4 hours. What that means for batteries is if you're primarily relying on solar to charge your batteries, would you ever make a battery that's more than 6 hours? You could never charge an 8 or a 10-hour battery if you're relying on solar to charge it. So you would basically need to stack a bunch of 5-hour batteries vertically to charge, and then deploy them horizontally to discharge so you can cover the peak. Is that the way people are thinking about it? And I guess that's open to Will, Gabe, Vic, whoever wants to field it.
Sure. That's definitely like taking a decrease in your capacity credit to take advantage of solar and discharge for a greater period of time later on is definitely something that we think about and we see happen in our model. I think part of this question really gets back to whether or not we're going to be 100% renewable or we're going to be 95% renewable and keep 5% gas, or how direct air capture is going to play a role in defining whether or not a system really is carbon neutral. If you can keep some gas around, I forget the gentleman that was talking about this in the first session, but if you can keep some gas capacity around, to provide power when you have these Dunkelflaut, yeah, for those periods, then I think to me that's the most obvious way, but it's just a matter of whether or not how the accounting is going to work, or what percent renewable really is 100% or carbon free. I think that is a question that is going to get shaken out politically over the next couple of decades, but I think that's going to play a big role.
I think that might also be the German word for when your dark beer goes flat.
That's probably the German word for Oktoberfest, or the start of Oktoberfest or something. I agree with what you're saying there. You really have to take into consideration, what the cost is of solar, because obviously if you're stacking those storage resources up and you need to charge them all at the same time from solar resources, then you're going to need to build more solar resources. So it's a question of trade-off between, well, do I want to pay to build more solar, or do I want to pay to build more storage? And that'll sort of give you the answer of what that duration needs to be. And then, of course, you've got variability in how that solar performs over the year. In the winter, you're going to get less off of it than you will in the summer. Again, you kind of get to that question of how much solar do I need to build? And when I build that quantity of solar, that should give me some sort of expectation for output. And then, given my gas availability, then how much storage resources do I need to pair that with, and how do I stack those, or how do I organize it? And those are questions we need to think about, and I think ultimately we'll be spending a lot of time, because that's where the dollars and cents of the investments and the actual build out of new resources is going to go.
Vic, you got any thoughts?
Nothing much to add. Just I think you make a good point, and just by looking at the solar resource, it is kind of limited into how much you can charge it, and then you're just driving up costs without getting as much of the benefit. But there can also be applications for when that might be feasible, as Will and Gabe were saying, in these high penetration scenarios. When either due to policy or other constraints, where costs become less of an issue.
So I think we were at the time that we notionally told people that we would be wrapping up. I think we technically have this line for a few more minutes. So I think I'll thank Gabe and Will and Vic for their excellent presentations, very informative. I think after we're finished with the wrap-up, if people want to stay on the line and get more questions in, we can probably do that to a little extent. But I want to quickly turn it over to Glenn to see if he has any closing thoughts for people who are expecting to leave at 4:15.
I think we had a question, Chris, actually, in the Q&A.
We can get to that after Glenn says whatever he says.
Okay.
Sorry. No, I went dark there with my monitor. No, I didn't have any questions. I found all the presentations very interesting. I have a lot of questions based on what I've seen. I thought Will and Gabe gave some very interesting points to consider. But I don't. I think I'll kind of defer to the group, and if there aren't any questions, then I'll offer mine. Mine more on the specific operations side. I don't know if that's the right. In other words, how deep do you discharge? How fully do you charge? I was intrigued that that CAISO operates these batteries, and I was wondering if there's enough history now that there's a sweet spot, that optimization strategies that maximize both the life and the economic value of the batteries are starting to become clear to people. But again, those are fairly detailed, specific questions. I don't know that I want to take up a lot of everybody's time with their consideration.
Well, why don't we get to the question that Andrew Benson asked, if hopefully he's still on the line. Any guesses as to how much storage would have been deployed in CAISO absent the TUC procurement mandate? And I assume that's primarily aimed towards Gabe.
Yeah, I think I answered the question to be, how much storage would we anticipate being on the system if we didn't have any CPUC procurement targets? And I think the CPUC procurement targets go hand in hand with the state mandate to get to greenhouse gas neutral electricity generation in 2045. So I think if you didn't have the CPUC specifically calling for procurement, I think it's doubtful you'd have too much storage developed at this point. But the fact that And I would just add that the CPUC is not calling out what technology needs to be developed. I think prevailing economics is saying that, we know we're going to need a resource. They are saying that these things have to get us towards the 2045 goals. So we know that renewables and storage resources are sort of, what's acceptable in that direction. But there isn't anything specifically saying, hey, you have to go out and get storage resources, and yet that's being secured. And I think a lot of that's driven by economics. So hopefully that helps.
Okay, thanks. All right, Glenn, you want to remind us what your question was?
Optimization strategies around battery operation. And so this does, we have seen a slight leveling off, if not a slight decrease, in the proposed durations of batteries that are coming online. So by 2024, currently the weighted average of duration of a battery is 1.5 hours. By 2024, we think it's going to be 4.5 hours. But it seems like those later batteries are not going much past that. In other words, if you were to plot that out, which I know would be helpful if I had charted that we're not seeing much of an increase past 4.5. In fact, it seems to be leveling off a bit, maybe going down a little bit. So I guess, Chris, that probably goes to your point. That is there a limit in which durations are that you find a limit in durations? Well, I guess my question is, how meaningful is duration if you find that battery operation is better handled by not fully charging, fully discharging, and in other words, you're stacking your batteries differently, not just because it's got a duration limit, but because you find that your asset is better managed with by either not cycling it so much or cycling it within a certain range. And at some point, we're going to have the operational history to see that. I was wondering or maybe we've already seen it. Maybe people have thoughts as to whether if that is to what extent is that does that apply?
Hey, Glenn, this is Gabe. You've hit on a lot of points where we've had a deep amount of discussion with our stakeholders and the developers of storage resources across the state of California. So I can speak to a little bit about that. I think I would start with the statistics. So So nearly all of the capacity that's installed in the state of California is 4-hour duration batteries. Some of the projects we have online only have 1 hour of capacity today, but they're expanding and building that capacity out to 4 hours. And the key driver of those resources being 4 hours of duration comes directly from the CPUC and the counting rules around resource adequacy that state you have to be available to provide energy consistently for a 4-hour period in order to count for resource adequacy. So if you're a 100 megawatt battery and you've got 400 megawatt hours of energy capacity, you can provide that full 100 megawatts all 4 hours, you count for 100 megawatts. If you've only got 100 megawatt hours, you basically count for a quarter of that because you can only provide 25 megawatts for that full 4-hour period. So there's a lot of financial incentive here in the state of California for storage resources to size themselves at 4 hours, because that's where you get the resource adequacy payments, and primarily that's where most of the financing of the project comes from. Looking at rules for other ISOs across the country, I think every other ISO has at least a 4-hour minimum requirement. I think there are some longer requirements in PJM. Maybe they go for like 6 or 8 hours. And maybe New England or somebody has maybe a 2-hour requirement. But other than that, we're looking at 4 hours for everybody else across the country. So I would expect that those rules that are put in place via the resource adequacy programs and how much these things can actually count for are going to be what's driving the sizes and the energy capacities of these new resources that are being developed in the future. Now, to the second part of your question, when we talk to storage developers, what they are saying for the batteries that they're developing here in the state of California are that most of them are specifically designed to perform around 1.0 cycles per day. So that's sort of where they operate the most efficiently in terms of things like cell degradation and the costs that are associated with that, the need for cell replacement and early cell replacement. And if they say perform 1.2 cycles per day, I think the additional marginal costs that they encounter from that extra 0.2 cycles can be pretty significant in terms of the dollars. Whereas if they perform 0.8, maybe they don't save that much in marginal costs, but they could have performed a little bit more and basically not incurred much additional cost. So it has to do not so much with what they're finding as optimal via the economics of the markets, but it has to do with how they're designed in the first place, which could have some inference from market results and those sort of things. So I think that's what we're seeing here in California, at least. And the final note on that is that when a storage resource is participating in our markets, basically they're putting in a bid curve into the resource, and if prices are high, we're going to be scheduling that resource to discharge. If prices are low, we're going to be scheduling that resource to charge. And obviously they have the latitude to change those bids around, but we don't really care whether or not that resource had a specific schedule in the day-ahead market, or whether or not that resource is best suited to perform 1 cycle a day or not. We have some additional tools that they're able to manage their state of charge with, but primarily what's still driving the charging and discharging decisions on a 5-minute by 5-minute interval in the California markets are what they're bidding and what the prevailing prices are.
All right, very, very helpful. Thank you, Gab. I appreciate that.
That's a great question.
So I think probably the last question, because I think we really are running low on time here. We have one from the chat box, or from the Q box. From an operational standpoint, how far down has CAISO typically cycled the storage resource? 20%, 50%, or some other level? As Glenn asked, are there cycling or degradation considerations taken into account when determining the depth of discharge?
Yeah, so the answer to the second part of the question is no. There is no consideration from the ISO's perspective in terms of the discharge. We do track stated charge, so we know what the batteries are, and if the minimum stated charge in a storage resource is 0 megawatt hours, we won't discharge the resource beyond that. But aside from that, we're not doing anything to say, oh, you're at 0.9, we're not going to use you very much after this or something like that. Yeah, the way that those storage resources get dispatched is how they bid into the market. And like I mentioned, there are some additional tools that we just introduced to help storage resource scheduling coordinators manage that stated charge through their bids. But it's basically how they're bidding and how prices at their location are materializing. And if those prices are high, those resources will get instructions to discharge.
Great. So I guess just to sort of wrap things up, and I'm surprised we still have, it's like 33 or so participants on the line. I think it was a very informative program, both sessions. I want to thank all of the speakers. Big round of applause. I think as a agency-wide takeaway, as I think Tom mentioned at the beginning, EIA uses these forums to sort of learn from our stakeholders what we need to be looking at in terms of developing both our statistical program as well as our analytic and projections forecasting program. I will certainly speak from the projection side, forecasting side, that I think we learned a lot that will be helpful in helping us maintain our models and develop the models going forward, because we are at a very challenging time. We're being asked to model worlds that just don't exist right now, but we can kind of see through places like California where they might be headed. And this, listening to everybody's presentations helps us figure out what we need to do to get there. And with that, unless Glenn has anything else, or Tricia, they want to say, I will.
I do not. Appreciate Chris. You did a good job managing the time there. So appreciate you keeping us right on time.
Yes, thank you very much, Chris, and thank you to all of our panelists today, as well as everyone who came out and attended. Hope everybody has a great day.
Thanks.
Thanks, Tricia.
Bye.
Thanks.